Good evening, all the participants.
Good evening, sir.
So we'll start our today's session once today's expert joins the meeting. So we'll just wait for 1 or 2 minutes and then we'll start the session. Dr. Ratna Parki, I have made you co-host. Will you please check?
Yes, sir. Yes, I can share the screen.
Dr. Ratna Parki, will you please check from your side? Are you able to share your screen?
I have shared the screen. Could you please confirm it is receiving?
Yes, now it is visible. Yeah, clear. Ratna Parki, sir, I think we need to wait for 2
Yeah,
more minutes
yeah.
because we have very less participants right now. So they may take some time.
Yeah, please.
Yeah, so once the sufficient numbers are going to join, we'll start the session.
Okay, okay, sir.
Okay. This is a very important announcement for you. Tomorrow we have all the sessions are going to start at 2 p.m. Please note. From 2 p.m. to 3:30 p.m. we have a first session by Mr. Suhas Lovely, sir, on rural community development through technosocial collaboration. Then from 3:30 p.m. to 5 p.m. we have another session on deep learning integration into crop disease prediction by Dr. K.B. Kanchandani, sir. And then we have the last session is there, that is from 5 p.m. to 6:30 p.m., which will be on the new technologies in agriculture mechanization by Mr. Sandeep Rajput. He is the technical lead at the John Deere. Then from 6:30 p.m. to 7:30 p.m. we have an online test and feedback will be there. So that test will consist of around 50 questions. The objective questions will be there, and you have to appear for the test from 6:30 p.m. to 7:30 p.m. And then from 7:30 p.m. to 8 p.m. we have a validity session is there. I request some of the participants, please provide your valuable feedback during the feedback session so that we can have the improvement in our future FDPs. Regarding the online test, we are going to share possibly today night all the recorded videos through the YouTube so that you can access these recorded videos and you can go through the test. If you have any queries, you can ask, else we will start with the session. Okay. Ratnaprati sir, will you please share your screen?
Wankhede sir, I have shared the screen.
No, actually, I have stopped from my side to share the schedule of the FDP.
Okay, okay.
Yeah,
So I'll
yeah.
stop sharing and reshare.
Okay, now it is clear. Your voice is also loud and clear. Yeah,
Yeah.
your video is also clear.
Okay.
Okay, so thank you. So good evening, all the participants. I welcome all of you for this day 5 of the faculty development program on leveraging cutting edge technologies for the sustainable agriculture practices, the organized by Chhatrapati Shahu College of Engineering, Chhatrapati Sambhaji. I am Dr. Praveen Wankhede, the co-coordinator of this faculty program, along with the coordinator, Dr. D.L. Boyar sir, and my organizing team. I welcome all of you. Now today we have again two sessions are there. The first session will be on low power IoT networks by Dr. Vivek Ratnaparki sir. And then we have a overseas expert session is there, the second session, that is by Dr. Pappu Yadav. He is the assistant professor at Dakota State University, USA. So without wasting much more time, I request Dr. Vivek Ratnaparki sir to start with his session. I think I don't need much more introduction, but I just want to say something because there may be a new participants. Dr. Vivek Ratnaparki is presently working as a staff engineer as in R&D at Tejas Network Limited, Bangalore. He has almost 17 years of academic as well as 3 years of industry experiences there. Mostly his work he is doing in RF and microwave, and he's handling different R&D projects at the Tejas network, which includes IoT networks or the RF and microstrip devices. So, sir, please start with your session.
Okay. Good evening to all of you. Thank you, Wankhede sir. All participants, as you know that this is a second session which I have been covering for this FDP. I just wanted to connect my earlier discussion to this session, and then we will move ahead and try to discuss some of the low power IoT networks. Before I start, because we will be, for the entire session, we'll be talking about low power IoT networks. So if coordinators permit and the chat is enabled for all the participants, I'll give maybe 30 seconds of a time to all the participants to chat, or if even if it is a possible, coordinator can unmute participants for a time being, and let me understand what is the understanding of participants related to the low power IoT networks. What exactly they mean or expect out of the low power IoT networks.
Yeah, we
You
have
can
given.
chat, yeah, or you
Yeah,
can
I have given the right to all the participants so they can unmute themselves.
yeah, yeah.
So any of the participants would like to say?
Or if you can chat in the chat box also, what is your understanding on low power? What do you mean by low power network? Any message is there? Wankhede sir, could you please confirm?
In chat box, there is no such question.
Yeah, yeah. Okay, so let me put it in other way. Because generally we would like to answer in terms of yes or no. Before I start with this contents of my presentation today, let me ask you something. Have you heard about Wi-Fi backscatter or YTAG? Some of you can just chat yes or no. Have you heard about YTAG or backscattered Wi-Fi? Whether anybody heard on the slim radio? You just have to chat either yes or no, so that I could get connected with some of the participants, because being online mode, it is difficult to get connected with the participants. So I expect some of the participants should get connected and try to answer in terms of yes or no. Have you heard on this concurrent technology?
Ratnabargi sir, are you able to see the chat?
Yeah, chat box. Some of the people are saying yes, yes, yes. So many people have heard on what? Concurrent technology? Okay. So I don't get afraid. I am not going to ask you individually, what do you know, what do you mean by concurrent technology? But all these terminologies are used in low power IoT networks. So this backscatter Wi-Fi, slim RF, concurrent technology, I'll try to touch on all these uh, aspects during my talk of this low power topic. So that stay tuned and try to pay some attention at least for 50-55 minutes. First half of my discussion, I'll try to cover on all these latest technologies which are very much useful in low power IoT networks. Rather low power communication networks, we can say. Okay, so with this brief effort to get connected with participants, let me start with the content slide. I'll start with the brief overview of IoT network. What do we mean by it? Then some of the agricultural environmental issues I'll try to address quickly. And then I'll jump in the concept of low power IoT networks or IoT systems. What do we mean by this low power IoT system? And then if you have to being a IoT engineer, if you wanted to design a low power IoT system, so how do you do that design? So that topic I'll call it as a optimized power consumption. So based on your expectations, or let's say your design requirements, you can optimize the power consumption of this IoT system. That case study I'll try to discuss in today's session. Then we'll discuss on role of IoT networks in precision farming, sensors used in precision farming, role of unmanned air vehicle in precision farming, and two case studies I'll try to touch upon at the end of this session. So this is how I'll going to discuss for today's session. So let's start with a simple slide. We have a agriculture as application. Now let's see, in India, this is the largest industry, and it is the sole provider of human food. There are a lot of issues related to agriculture in India. So generally farmers are not using the educational enhancements or educational upgrades happening in the field for the farming. So because of that, they are not able to achieve the required or expected yield out of their farming. So some of the challenges I have listed and the possible solutions, if you could just quickly go through all these topics. I'm not going to explain this because I just wanted to give you some idea on the agricultural challenges and possible solutions. But the last segment, which you can see here, which is about education and awareness. So the IoT comes under this particular sector, wherein we can educate the people, use the technology, and improvise the yield of farming. So with this brief, let's directly ask a simple question to ourselves. What do we mean by a precision farming? I'll be more than happy if somebody could unmute and answer this thing, or even if you can chat in the chat box. We'll just take a 10 seconds of a pause. The intention behind asking the question at the start, many of participants can get some breathing time and join. And at the same time, I'll try to get connected with some of the audience. That is the only intention. You might be knowing this, you might have carried out certain projects in this field, but there are some beginners who would get benefited out of this discussion. So that is the only intention behind putting these simple slides. Okay, so let me take it in. Is there any precise usage of resources in farming? Absolutely right. So how do we do that? Precise uses of resources in farming, that is what precision farming. A literal word meaning of the precision farming is that. So using these resources, but at the same time, you see, you are using the resources precisely, but you have to increase the yield of crops and make the farming more efficient and sustainable. The latter predicate is more important. If you use the resources precisely and you are not focusing to improvise the crop yield or make the farming more efficient as well as sustainable, then that won't make any sense. So we have to answer it in a complete way, using resources in a precise manner. That will be only possible with the help of technology. And at the same time, we should focus on the increase in crop yields and making farming more efficient and sustainable. I hope this is more apparent definition and it is a comprehensive definition which will be accepted by all audiences. Now, let me go ahead and try to explain in further technical details how do we do this thing in precision farming. So there is the concept called as a 5 R's. So the first R stands for the right input. So let's take a case of nitrogen has to be used for farming, and based on the input of nitrogen, your crop yield is going to uh, you can take the crop yield based on the use of nitrogen. So you have to use it in an optimum way. It should not be like that you are using it too much nitrogen or too less nitrogen. You have to use it in an optimum way. That is what we used to call it as a right input. So that is the first R. Second R, let us say the other resource is water. So water resource, but we should consider the overall farm field. Let's say there is some sandy area or some overlapping pivot is there or some roadside area wherein we have to control the water irrigation. We have a pond or some muddy area is there in the farm. So based on the geographical conditions, it should not be the case that in all areas we have been irrigating the same amount of water. So that is not the precise farming. That is, in some cases, you may be needing, let's say, 10,000 liters of water, but you are irrigating more than 10,000. Maybe in some cases you need, if it is a pond there, so you need, let's say, some less amount of water. So based on the geographical condition of your farm, the water irrigation has to be controlled in a required way. That is what we used to call it as a right irrigation rate. The first is right input. Second is right irrigation. Third is right time, right input application time. So what does it mean? Let's say there are two pictures. You have been using the nitrogen for different crops. So when crop is growing up, it doesn't need lot of amount of a nitrogen. Let's say 5% is sufficient at the seed level. But as the crop is growing up, growing up, you have to increase the nitrogen input based on the growth of crop. Let's say in the middle, you can increase it from 5 to 25. When the crop is getting further growth, so you have to increase the amount of nitrogen input, let's say. So this is how you can control. This is generally done by farmers. They know when we have to use what is the amount of nitrogen or the fertilizers to be used. So they use this technique, but what is the right amount? What is the percentage they have to use? Even though they know it, let's say if they have used the nitrogen and there was a rain, so that is not in a control. So this can be beforehand. We can predict the weather conditions and somehow we can improvise the fertilizers or nitrogen application to the farming. That is the third R right time. The fourth is right placement. So if we are, let's say again, the same case, I'll use nitrogen only we have been using. So nitrogen utilization efficiency, if you are not putting the nitrogen in the respective places where it is actually needed, likewise the place which is shown at the right side. So the some percentage, maybe 10 or 15% of nitrogen will be getting wasted out. So that is not being considered as the precision farming. So the fourth R is right placement. And the fifth is right manner. How you are doing a farming with different cover crops you have been using in between. So you are utilizing the area which is not used as a major crop, but the in between rows you have been covered with some other crops. Then chemical herbicides and mechanical manners can be used to improvise the crop yield. So these 5 R's, I just wanted to let you know about the precision farming: right input, right irrigation rate, right time, right placement, and right manner. So these are resulting into the precision farming. Okay, so IoT overall picture, we have discussed it many a times, so it can be used in multiple applications. Though our focus is agriculture, but it is being used mostly everywhere nowadays. As I said that during my first session, agriculture is the very small portion for IoT applications. So typically it is around 4%, but moving ahead some 5-10 years down the line, people will be using this IoTs for agriculture, and this percentage can increase with the help of low power applications, which we'll be going to discuss. Okay. With this brief, now let me start with the actual topic, which is IoT network. So how this IoT network will be built up, or what are the entities present in the IoT network? So as you can see, there are different IoT elements. The first entity is IoT elements. Then there will be certain architectures. I'll cover all these topics in further details as I move in my presentation. So these are the 4 entities one has to consider when talking about the IoT network. So elements, architecture, operating systems, and channel. So these are the IoT network systems. Okay, what do I mean by IoT architecture? Elements I'll cover on the next slide. So these are the different IoT architectures, but generally this 5-layer architecture is being most popular, as you can see the D number figure. So objects means your sensors which you have been using, let's say temperature sensor, humidity sensor, moisture sensor, something like that. It is being covered in this particular layer. Then we have object abstraction, service management, means how the data can be transferred from that sensor to the node, from node to the particular receiver, and that way it will goes to up to business layer, wherein that data can be used for further predictions and analyze and predict the farming. So this is how the IoT architecture goes. Please excuse me, I am not going into the minute details of all these factors because our objective is to understand low power IoT network. So I'll just quickly touch upon all these entities and directly go to the low power IoT networks. So IoT elements, what do I mean? That was related to architecture. Second segment is IoT elements. So identification means some, let us say RFID or Bluetooth or Wi-Fi, that is typically called as signal identification. So that is first block one has to consider for IoT element. Second is a sensing. So how that data is being sensed. So physics involved in between. Then we have a communication. So once you have gathered the data, you have to send it to some nodes. Then that data has to be computed and services has to be offered, and semantics. Semantics is typically a brain of your IoT elements, which takes care of all this data and processes. Then different operating systems. The most popular one is Android. The language support, the event-based programming or multi-threading. Multi-threading, I mean here, the parallel processing, which are they're possible with this operating system or not. That is the meaning of multi-threading. So all these operating systems are quite popular. Out of that, mostly I have seen Android is being used for IoT networks. So the standards being used for IoTs, you can see there are different application protocol standards. Out of that, MQTT is quite popular one. HTTP is also there. Service discoveries are there. Then infrastructure protocols related to different layers. For our application is IPv4 and IPv6 are quite popular, which is a low power wireless network. So apart from that, for link layer, we use 802.15.4, which I have shown during my earlier session on yesterday. So 15.4 is related to the Wi-Fi and Wi-Fi hollow kind of a thing. So that we will discuss in upcoming slides further. But you can remember with respect to the layers, there are different infrastructure protocols. All right, similarly, IoT elements and their samples. So you can see I have listed here identification and the samples. Sensing, we have different sensors. Communication, this we have discussed yesterday. So computational, we have hardware as well as software. So these are all the computational elements. Services and semantics. So all these things are involved in IoT elements. I am not, again and again I am saying I am not going into the details of all these aspects, but for the sake of consideration of all the participants, for every slide I have given some reference. So anytime if you feel that I just wanted to get more information on this all topics, please go through this reference or do not hesitate to ask me question at the end of session. I'll take you to all these references and we'll discuss more on all these topics, because due to limited time and the topic which I have planned today, I'm just going to the exact topic, which is a low power one. So NB IoT overall picture, as you can see, yesterday we have seen the pictures of IoT market. Now I am focusing on NB IoT because it is a low power wireless standard. So by 2023, it is expected that US dollar 2.6 billion is the market for NB IoT. But by the end of 2030, it has been expected 37.6% growth in this particular market forecast, which is close to 24.6 billion. Yeah, somebody's. Okay, if there is no any question, let me go ahead. If you have anything, please don't bother to interrupt me in between. So I tried to answer the first question, precision farming, 5 hours. I tried to cover what is the IoT network. I have tried to give you some glimpse on that. Then what is low power IoT? IoT elements we have discussed, and now our main topic is low power in an IoT. Similarly, I'll take a pause of 10 seconds, and if somebody would be interested to answer this, please chat it. What do you mean? What do you mean by low power in an IoT? Any clue on that? Okay, so let me check. Less use of IoT technology. Is that somebody saying? Is that the real meaning of low power? I'll try to take a couple of more chats so that I can connect with the participants. At least 1 or 2 more chats I expect from messages from audience. What do you exactly mean by low power? Please try to answer it out. Otherwise, my next slides, you won't be able to connect. Yeah, I'm getting some messages. I'm very happy. Minimal energy. Okay. Device having power supply, power consumption less than milliwatt. Very happy to see these things because something is coming out. See the terminology power consumption. I'm very happy and appreciate the chats given by some of the audiences. Devices having power supply. Okay, that is okay. Battery backup, minimal energy, minimum energy resources, lowest power consumption. Yeah, that's all answers are correct. Right? Good. Thank you. Thank you. So let me come back to the topic. See, I have tried to answer this question in this way. Let me know if you are agree or disagree with my statement. Low power IoT devices are generally built in such a way that they do not drain a lot of power. Means your device, your system will work with minimal power resources. But at the same time, it is providing the level of functionality and performances expected of them. So you are not compromising on the functionality and performance of the system, but at the same time, you are operating your entire system with bare minimum power. That is what we used to call it as low power. Somebody had said that in milliwatt. So coming to that particular chat, low power consumption in milliwatt. See, all these low power IoTs or even little higher power IoTs will work on the power consumption of milliwatts only. It won't work in watts or something like that. But nowadays, you will appreciate when I come to that particular picture, I'll show you. I'll not only use the word low power. Please mind my words. I'll use the word ultra low power. I'll say that there are many IoT networks which are consuming power is in terms of nanowatts, not even in milliwatts or microwatts, in terms of nanowatts. So please pay your attention for 30 to 40 more minutes. As I said, initially I said 50-55 minutes. So I already consumed your 10 minutes of a time. But after 30-40 minutes of a time, I guarantee you will be able to design or optimize your IoT communication system based on the power consumption requirement. So those formulas I'll try to share with you just within a 10-15 minutes of a time. Okay, so with that, how do we control the power consumption? How it is possible with different IoT networks or IoT devices? So let me go to the next slide and let you know that based on the modes of operation, the power which is being taken by a particular IoT device is going to vary. That is what we used to call different power modes present in the IoT devices. So first mode, as you can see on the screen, it is an active mode. In this particular mode, the entire device is functional and it is able to transmit the data, receive the data, and all the low power IoT sensor activities will be on. So they are functional. That is what the meaning of active mode. And in this particular case, you can see the power consumption will be the highest as compared to the other modes. And reason is that all the entities, hardware, software, everything will be on and it will be functional. So this is the first mode. Other mode is that we used to call it as idle mode. Idle mode, in this particular mode, the processing will be minimal, or we can say the no processing is currently taking place. So that mode is called as idle mode. The device is configured in on state, power is on, but the processing will be bare minimum, or either we can say there is no processing happening at this particular mode. Whenever it is required, the processing can be started. That is what the idle mode. So compared with the active mode, idle mode is going to consume a lower amount of a power. The reason is that the actual signal processing is not being happening and some resources are being switched off. Again, if you wanted to reduce the power consumption, so the third mode of operation of the IoT devices is sleep mode. In this particular mode, device will be off for a particular time. That is what we used to call it as a sleep time. So devices will be sleep or off for a particular time. So most of the features of devices are powered off, or we can say powered down. So only few circuits and utilities will remain on to watch the specific states or signals. And once it is expected, the device will get wake up and rest of the device will start to operate. So this is the sleep mode. Then because of this, it will greatly reduce the power consumption, because battery life of the devices will be significantly enhanced using the sleep mode. So this mode is very useful for devices that are intended to operate for relatively longer periods on a battery power supply. If continuous on is not expected, I'll take some of the cases wherein it is used for in a sleep mode or what. So it will be known to you. So higher the sleep mode, more will be the power optimization and power consumption will be less. Then we have a deep sleep mode. Let's say we are keeping the device shut down for almost all operations. So that is what device is in a deep sleep mode. So in this particular mode, the power consumption will be again very low compared to all other earlier modes. And now somebody was saying in milliwatts, you can see the power consumption in deep sleep mode is in microamperes. But I said that the power consumption of IoT devices can be greatly reduced up to nanowatts even. Okay. I'll take some of the calculations for milliwatt kind of a power consumption. Okay. And I'll show you some of the IoT devices and controllers based on their power consumption capabilities. So what is exactly the low power, you will understand when we do certain case studies. And the last mode, which reduces the power consumption greatly, wherein the device turns off practically and all functions and controls will be off. Just a non-volatile memory is there and the information will be saved in that memory, and whenever you ask, the device will start again. That mode is called as hibernate mode. Okay, so for this particular mode of operation, there is almost device is almost off, so very low power would be used. That is what I just wanted to let you know out of this slide. And now let's go to the next slide and try to understand what are the hardware components are going to be controlled based on the modes. So the mode which I was calling idle mode, here it is a mode modem or a sleep mode, then idle mode, then I called a sleep mode, and then deep sleep mode. So this is sleep, this is deep sleep. Same 5 modes of operation are here. So CPU, Wi-Fi or Bluetooth, your wireless module, then RTC memory and peripherals and processors, everything will be on in an active mode. When you go to, let's say, sleep mode or idle mode, you can call it as, because we called it as idle mode on earlier slide. So your Wi-Fi module or Bluetooth or maybe a wireless module will be off, but rest of the things, rest of the hardwares will be on. So the power consumption with respect to that will be minimum. Then in this sleep mode, the CPU will be paused. For some time it will pause, and then after a certain amount of time, based on the programming, that will going to turn on. So it will again reduce the power consumption. Then we have a deep sleep mode, wherein only some of the memories and peripherals are on, and this processor will be on off for a certain time. The CPU and wireless module will be off. In hibernation mode, all these things will be off. So only the part of memory will be on, volatile memory, that is also. So this is how the low power mode IoTs will work. With respect to the modes, now you can see the description. I'm not going into all these units. Don't worry about all these units, just focus on the power consumption. In active mode, if RF is working, means the discussion which we had during our last session related to the radio frequency performance. If RF signal is being transmitted and received, the amount of power consumption will be pretty high, in the range of few tens of milliamperes. That is the current consumption. If you multiply with the applied voltage, let's say 5 volt, 3 volt something, you will get the power consumption in milliwatts. So we'll do that, as I said, we'll do those calculations maybe in 10-15 minutes of a time. So sleep mode, let's say idle mode, the current consumption will be very less, 20 milliampere at the max. Then we have a light speed, deep speed, hibernation mode. So you can see even micro amperes of current consumption is there. So that is very much possible. So the source, I have taken this from ESP32 datasheet. If you want, you can note down this link or can go through this particular website to get the more idea on this. So let me quickly go through this particular power consumption picture. I have different modes on x-axis and I have current on y-axis. Even you can plot the power based on your bias voltage. Current will get multiplied with the voltage, and you'll get the power in milliwatts. See, the active mode. Active mode, we have two different currents. I'll talk more on the static current and dynamic current. So this dynamic current is one which is going to change, but static current is always there in your circuit, electronic circuit. So how do you control the static current to reduce the power consumption? But in a very simple way, you can see that in active mode, the power consumption is very high. As you move on from active to hibernate mode, the power consumption will be very low. And same explanation is there with respect to earlier two slides which we have. Okay, now let's come to the design objectives. What we want the lower power consumption. See, this is very important to let me mark here. Our main objective is low power consumption network has to be there. But when you go for a low power consumption, you have to compromise certain objectives. Let's say wide coverage. When you say low power consumption, if you remember from my earlier discussion, I have did a case study related to the link budget. If I reduce the transmitted power, if I reduce the antenna gain, that will be resulting into the lower power consumption. But it will affect on the coverage. So coverage won't be possible. So both these parameters will not be possible to achieve in one network. Either you can focus for lower power consumption, or you can focus for wide coverage. If you have to get a wider coverage, you have to increase the power. What amount of power you are feeding to your IoT network. But how do we compromise? That is what the optimum design. Optimum design means power consumption and coverage. Both should be optimum. Not only these two parameters, but also you can see the QoS. What do I mean by QoS? Hope you remember, I have devoted some amount of time to discuss the quality of service parameters for any IoT network. Those parameters are latency, throughput, data rate, all these things. So reliability, that all parameters comes under the heading of quality of service. You don't want to compromise this also. At the same time, scalability. Your IoT network, though it is a wider, low power consumption, quality of service is good, but it has to be scalable, can be connected to the number of devices and can be transformed to any different protocols and communicate with external world very comfortably. That is what we mean by scalability. See, all these wireless communication protocols are going to work in the typically in the band of 2.5, 2.4 gigahertz. So because of that, there would be a lot of interference. I'll show you some of the pictures about this thing. So unintended signal will be present. It will be interfered with your intended signal that will cause some interference. So interference management has to be taken care. Even if you take care of all these objectives, the last and most important one is the cost of your IoT system. If you try to achieve all these objectives, you have to pay little higher cost. That is what we have to understand from this particular picture of the objectives for low power wide area network design. Okay, so let me quickly go to the next slide. And how do we achieve this? So in many situations, IoT devices are powered by batteries. That is well known to all of us. And power efficiency is the most crucial need for them to operate reliably for a long period of times. Let's say take an example of amplifier. If the efficiency of amplifier is higher, or even your mobile phone you can consider. If you charge it in the morning and you use it continuously throughout the day, when you go back evening home, you have to charge it again. Why? Because you have used it for a longer time. So what do you want? You want the longer and longer battery time. So who will decide the duration, how long the mobile phone battery will be going to stay or operate? What is the important block? People say that this is a 3000 milliampere hour battery. This will last long for 24 hours, 30 hours, 50 hours, like that. But what is the electronic component or electronic circuit which is going to decide the battery reliability for a longer time for mobile devices? That is that is none other than your amplifiers, rather power amplifiers we used in mobile phones. If you use a particular semiconductor technology, the efficiency would be more. More the efficiency, power consumption would be less. And power consumption less, longer will be the operating time of that particular electronic gadget. So that is what we have to focus on. Okay, let's come to this picture and try to understand the IoT system problems. The first is the power consumption, which we have been trying to discuss since last 8-10 minutes. And second problem is the increased system lifetime. So we have to have a lower power consumption and the larger and larger or more and more system lifetime has to be there. So these are the major problems IoT engineer has to address. So how to do that? What are the solutions? Let me take again 10 seconds of a pause and try to get connected with my audience. I have opened up the problem. I shared that what is IoT network, what are the problems with IoT networks, what do we mean by low power IoT networks, what are the challenges or problems in IoT networks. So can somebody help me to propose certain solutions over this? Couple of chats from your side. So I'll feel happy and get an understanding you all are on the same line where I just wanted to take you. How do we go for low power IoT design? What are the solutions? Don't say that I'll use a Bluetooth low energy, I'll use the wireless protocol which is consuming a lower and lower power. Is that the only solution? How do we design a low power IoT network? Yeah, the first chat. I hope at least 10 messages I'll get. Supervisory controlled, topology is the first. What do you, topology you mean Wi-Fi, Bluetooth low energy, NB-IoT, LoRaWAN, something like that? I already said yeah, I already said don't message that because that is what the customary. Even a non-electronics or non-IoT people can say that I'll use the technology which is consuming the lower amount of power. But being IoT designer, what is your solution? Okay, topology again is the star topology coverage. Okay. Okay, go ahead. I'll take a couple of more chats. How do you design a low power IoT network? What are the solutions? Have you ever thought of that? I'll ask coordinators to offer some goodies for a correct answer. Hope Vankade sir don't mind. Hybrid solution. Okay. Data transmission. All right. Link optimization. Okay. Great. Couple of more chats. How do we design a low power IoT network? This is the most important question of today's session. Couple of more answers I expect. Less than one. What is that? Low data rate. Okay. Oh, no, we should not compromise on the quality of service parameters. That is what I have discussed for last 10 minutes. We don't have to compromise on range. We don't have to compromise on QoS, scalability, cost. Everything is expected with low power. Reduce switching frequency. Yeah, okay, that is one of the solution. That is not the everywhere means this is not the only solution. You can operate your device in different modes. That is what I have discussed. Different modes you can use means sleep mode, deep sleep mode, hibernate and all that. Okay, two more options for designing the low power IoT networks. Last two. Okay, thermal aspects. Okay, last one. Use a PWM controller. Happy to see that different answers. Thank you. Thank you. So please pay your attention. I'm very happy. People are quite interested to interact. I'll take 5-10 minutes of a time at the end of today's session to get interacted with some of the interested participants. Okay, so let me propose this. So this is the most important part of our today's session. I just want 10 more minutes and you will get most out of this session. So I'm going to propose some of the solutions out of my studies and these are likewise. If you disagree, please let me know. There are 4 ways of reducing power consumption. That is not the only one way, as you are saying, using the communication protocol, or somebody is saying reduce the power consumption using the range reduction, or use some topologies. These are the one of the ways of this thing. But as such, there are broad categories. There are 4 ways of power reduction. How do you know that? What do I mean by all these 4 ways? Let's say first mode of first solution, you can say circuit and processor level. You can design your electronic circuits or processors which you have been using in your IoT network in such a way that it will consume a lower power. We are not talking about any wireless communication protocol. We are talking about the controllers and circuits. What do I mean by that? Pay your attention, you will come to know that all these aspects within a 10 minutes of time, what I actually wanted to convey. So circuit level and processor level kind of a prediction. Let's say there is a concept of ultra low power transmitters, and they have been used in IoT since last 5 years. They consume very low amount of power. One of the possible solution, as I said, that there are 2 types of current in active modes. Hope you remember just before 7-8 minutes I said that there are 2 currents in active mode. One is a static current, other one is a dynamic current. So whenever the circuit is operating or signal processing is happening, the dynamic current will come into the picture, but the static current is always there. If you could interrupt the path between ground, or the current, static current is going to the ground, that will cause some power consumption. If you interrupt that path, you are going to save some amount of power. That is one solution which straight away comes into my mind to reduce the power consumption. So I'll just hold on this slide, and I'll take you to some of the important aspects. Yeah, I just wanted to take you to the next slide. Again, I'll come to slide number 20, but let me go directly. I don't want to play that animation. Let me tell you, because I said that even nanowatt or even less than that power consumption radios are available in the market. Now you will ask me the question, why you have written receivers only, why not transmitters? Because transmitters generally work on the higher power. You don't have a lot of options to reduce the power consumption in transmitter side. But for receiver, you can work on the power consumption very well. And the concept is that ultra low power receivers. You can refer to this particular IEEE publication where different ULP, ultra low power receivers, since 2005 to present have been reviewed, and their power consumption with respect to sensitivity in dBm is being proposed. So you can find that even less than 1 nanowatt of power consumption receivers are nowadays available. Even in the range of, there are a lot of, even some few tens of receivers are available. Those are consuming the power in the range of nanowatts. Mostly all these devices, as you can see, there is no device which is going to consume the power in terms of watts. They are all consuming the power less than 50 or 100 milliwatt at the max. That is what I was trying to tell you at the beginning of my discussion on the low power. Okay. Now this slide is let you know how do you design ULP radios. Okay, they are there, people are doing the research, they are proposing certain radios, but how do I use this technology in my IoT project? Or what are those technologies in further details? And then I can do some review and decide a particular radio or a controller or even a device for my IoT project. So the first is Wi-Fi backscatter. There is a very useful terminology in case of a Wi-Fi. As I said, it is a white tag. What is a white tag? The concept of this Wi-Fi backscatter, I'll tell you. Let me first quickly go through the new radio architectures which will be used for ultra low power IoT networks. Second is slim radio concept. This is what I asked you at the beginning of my session. Have you heard on this Wi-Fi backscatter or white tag? I'll touch on that. Have you heard on slim radio? What is this? Have you really heard on slim radio? Anybody? What do you mean by slim radio? No. So I like the honesty, because somebody said that I have heard on slim radio. I'm damn sure you have not heard on the slim radio. And the next term, which I'm tossing up here, is the concurrent technology. Have anybody heard on this concurrent technology? So these are the things which we use to come up with the ultra low power IoT networks. Okay, so let me jump into one after another of all these technologies which will be actually used in low power IoT networks. What is the concept of Wi-Fi backscatter? If you are really interested, I will take you to the particular literature documents, and therein we can discuss more on the low power architectures and these networks. But let me go with my presentation first. I'll just let you know the concept of Wi-Fi backscatter. See, if we use, let us say, this Wi-Fi backscatter concept or white tag concept, you heard about RFID tag, right? RFID tag we use for a signal, will receive certain signal. Based on that, we will try to analyze the data. For that purpose, we need RFID transmitter, and essentially RFID tag has to be there. But this YTAG concept or backscatter Wi-Fi concept, both the things are same only. If we use that concept, we did not to use a separate RFID receiver. The signal being transmitted by a Wi-Fi module will be backscattered, and that will be catched at receiver. So that is what the concept of Wi-Fi backscatter, right? And based on that, your power consumption can be reduced in few tens of microwatt. So that is the concept. Whether it is a realizable or not, that is other question. But people have done certain experimentations based on the concept of YTAG, and there is meaningful literature available for this thing. And they have proposed we can minimize the power usage as compared to RFID by using this YTAG kind of a technology or Wi-Fi backscatter kind of a technology. So that is what I just wanted to let you know about the first topic. Second is a slim radio. See, slim radio is what, again, you have been using a Wi-Fi. So instead of using your commercial off the shelf, the term is called as a COTS radio. COTS radio means conventional kind of your radios you have been using. So that will consume the power in few tens of milliwatts. So instead of that, this technology, slim radio, will use as a bare minimum hardware. I'll let you know what do I mean by bare minimum hardware and what is the COTS radio. I'll clearly make some difference between these things. If you use the slim radio, the power consumption is going to be few tens of microwatt, which is earlier in the case of COTS radio, it would be in few tens of milliwatts. So this is what the concept of backscatter and slim radio. Let me put some light on this slim radio only with respect to the earlier COTS. So this is what I was talking about. The COTS radio actually having these components: DAC, oscillators, PLL, voltage controlled oscillator, mixer, all these things. And the most power hungry component is PA. So this is the typical COTS radio, and is going to use the OFDM and quadrature amplitude modulation kind of terminologies to transmit the signal through to the COTS Wi-Fi. So this is a typical commercial off-the-shelf kind of a Wi-Fi communication. And note the word symmetric. What do we mean by symmetric? Let me put it in a very simple way. I am speaking in English. Somehow my language is not up to the mark, but you are getting something, let's say 70-80% you are able to understand because you also know the English. This is what we used to call it as a symmetric communication. But if I use some other technology, let's say slim Wi-Fi or slim radio kind of a technology. So what does it mean? So slim Wi-Fi or slim radio, you can see the number of blocks here are, you can count 1, 2, 3, 4. And here there is only one oscillator is being used. Ring oscillator switch is there. And then you don't have any option other than using the PAs. So that is why my topic of research was PAs. Anyways, you go to IoT, mobile, satellite, anywhere, radar communication, you don't have option to replace PS. So sorry, I don't want to deviate from the topic, but the crux of discussion is that if you have a conventional or commercial off-the-shelf receivers, you have multiple blocks to be used. You don't have any option. And since you have multiple hardware architectures, the power consumption will be high. You don't have any option to minimize the power consumption. But if you go with the slim Wi-Fi, the number of blocks will be reduced and you can reduce the power consumption. That is what the meaning of the slim radio. But there are the life of slim radio designer is not simple. There are a whole lot of challenges. The first challenge which you can see, the word asymmetric. It is something like that I am speaking in Chinese and you are not knowing the Chinese. That is how your slim Wi-Fi radio is going to get connected with COTS Wi-Fi. Okay, so for that, the solution is OOK kind of a modulation. That modulation is there and asymmetric kind of thing has to be there, should be used with this particular slim radio. So I'll take you to the next slide to talk more on this particular slim radio. So you can take away from this particular picture. If you are doing a commercial off-the-shelf Wi-Fi, then you have more number of blocks, so power consumption would be more. They are using some different type of modulation. And when you wanted to reduce or switch to the slim radio, slim Wi-Fi radio, number of hardware blocks will be reduced, power consumption will be greatly reduced. But the problem is that how do you communicate with your COTS Wi-Fi? So the solution is that you have to go with some typical kind of modulation schemes without any additional hardware and software requirements. So these are the challenges. First is incompatible modulation, then large frequency offset and low signal strength. So I'm not going to focus more on this COTS radio and slim radio. Our topic is a little broader one, wherein we are trying to understand the low power or even ultra low power IoT networks. But these are some of the concepts which you can keep in mind to understand these things. So COTS radio will have more number of blocks. So power consumption will be in milliwatts, tens of milliwatts. But since the blocks would be reduced, the power consumption will be very low in terms of tens of microwatts only. So this is what the meaning of symmetric and asymmetric. You are speaking in some language and the receiver is able to understand your language and you can get the information. But in case of slim radio, you don't know the dog is barking or the dog is asking for some food. So that is what the problem. So based on certain demodulation techniques, see, these are the two users speaking in same language. That is what we used to call as symmetric kind of a communication. But in case of this slim radio, the language of slim radio will not be understood by COTS or vice versa. So that time we have to introduce some kind of communication technology. That is what OOK is there. It is going to understand what actually the dog is asking for, whether it is a barking or asking for a food. That is what we used to call asymmetric kind of a communication. So without using any additional hardware or software resources, this slim radio concept is going to use or communicate with the COTS Wi-Fi access point. This is the picture of slim radio RF local oscillator, and this is the IC tape out of that radio verification. And the table is given to compare the power consumption. So the power consumption at transmitter power was 1 milliwatt in prototype. Simulated and fabricated ICs have shown the results which are very appreciated. Less than 100 microwatt power consumption is there for a fabricated IC. So this is the first technology which I just wanted to share with you. And you can see the good put or your throughput data rate, you can say, with respect to the range. Up to 30 meters, it works very well. Bitrate is few tens of kbps and range is few tens of meters. Let's say 30 meter is the maximum range which we can achieve, and that is good enough if we consider any Wi-Fi application. So this slim Wi-Fi has been compared with all other ultra low power state-of-the-art communication solutions. As you can see, lot of things are there, lot of literature is there. You can pick anyone, let's say Bridio, you pick passive Wi-Fi or Hitchhike, all these things are there. That is why I have mentioned a lot of references on my almost all slides so that we can go back and go through this literature and try to understand how power consumption has been achieved. Okay, now I have to go back. I don't have to forget about, I have left my earlier slide somewhere in between. This was the first solution. What? Backscatter reflex or ultra slim radio. Let me go to this particular paper and hope you will allow me to go over this paper for a few moments. Why I wanted to open this paper here? Because some of you might have a thought that yesterday we were discussing something on the radio link budget and some link budget calculations and all that, where it stands when I design a low power network. So you can see the title of this article. It is ultra low power radio architecture for IoT applications. And as you know now, asymmetric communication has to be used for the slim Wi-Fi, because slim radio has to communicate with the quartz Wi-Fi, and they both should interact with each other on the same line of language. That is what asymmetric communication. So you see the word here. Hope you can see this clearly. Link budget. If you read this statement, transmit power by around 80 dB while keeping the similar link budget. So link budget is very important. Itself in abstract, it is being written. You have to maintain the link budget. Link budget is all about the range, what you are talking about for your IoT network. And for IoT network, always range is important. You might be talking in terms of a range. I was talking in terms of a link budget. That is what the only thing. You have to make a note of this. I'm not going to the further details of this thing. I have covered maximum things which I could with this minimum time. Now let me go back to my presentation. This radio I covered. Now the last technology which I just wanted to touch upon is the concurrent technology. Concurrent means simultaneously. So whole lot of options are there. Quoro is very popular semiconductor industry, US based industry, which have come up with the low power IoT solutions. If you want, you can go and see this video. For the time being, I am not going to play this video. It is not available on YouTube. So you have to note down this site and go and try to see this 2.5 minute of a video, which will talk about the concurrent connect technology. But in brief, I'll try to tell you what does it mean by a concurrent technology. I have already downloaded. These are the number of Thread, Zigbee, Bluetooth kind of devices available from Quoro. They all work on a low power multi-standard wireless applications, maybe for homes, security, sensing, different applications you can use them. See, so you can pick any data sheet and study it further. And there is one development kit they have been given. So I have already downloaded it. Let me go to my particular folder and quickly I'll show you a couple of these things, so that the first product brief, this again talks about the same concept. I first will try to make it very apparent to all audiences. What do we mean by concurrent connect technologies? Concurrent, three things are simultaneously happening. One is antenna diversity. Again, you'll ask a question. What do we mean by antenna diversity? Let's take one by one. Antenna diversity, multi-radio and multi-channel. All these three technologies are being simultaneously, that is what concurrently, being used for this system on chip for this particular product. And hence they are calling this as a concurrent technology or concurrent connect technology. So being using all these things, what you can do, if you remember, what is the major challenge? I'm very sorry to the coordinators and audiences, because what I'm doing. Can you notice? I'm opening my yesterday's session. I'm extremely sorry. Why? Because I just want, as I said, I wanted to connect you with my earlier presentation. So you may remember that I said that there are certain challenges. It may be somewhere here at the start only. Certain challenges I have discussed. Yeah, the challenges. Can you see? This was the point which I was focusing. This is the major challenge. What is it? Standardization. No one had asked the question. No one had tried to get some more idea on this. I know this is not our regular class. There are many experts are attending this workshop. But see, this problem, if we do not solve this problem, how we move ahead with the IoT applications? If you are talking about the agricultural applications, if the standardization is not there, how we use IoT for last mile applications? So the problem is that we could use the different protocols in same IoT network, common protocol, common guidelines. And this is what the problem definition Quoro has taken up, and they have come up with the concurrent technology. The solution for this problem is concurrent technology. This was one of the challenges, right? So let me come back here somewhere in this. Yeah, the concurrent technology they have come up with. Whether I have opened the data sheet? Yeah. This is the, so you can see Bluetooth, you can work Bluetooth, Thread, Zigbee, Wi-Fi, all these terms can be used all together. So this is the architecture they have proposed. You can see very clearly, sorry, you can see very clearly Bluetooth, Zigbee, Thread, Master, everything can be used all together with this particular concurrent technologies. And it is consuming very low power. So some numbers I just wanted to show you. I'm not going into the particular details of all the parameters, but you can see ideal current consumption 0.6 milliamperes. Then you can see for 802.15.4, this is the Wi-Fi standard, which I discussed yesterday. With single antenna, now I'll come to the antenna diversity also. If you use the single antenna for communication, it will consume such amount of a current, very less current. But if you use multiple antennas, so that diversity will be there and there will not be any kind of a signal loss, information loss will be there, no possibility of information loss. So use multiple antennas. That is what we use in 5G also, MIMO. So this antenna diversity they have used, but at the same time, it is customary that if you use more number of antennas, the power consumption would be more. That is what, if you multiply with some number, as I said a couple of times, you can get the power consumption. So this is what antenna diversity, multiple channels, all these things can be used together. And that is why it is called as concurrent technology. So let me come back. There is one development kit also. If you are really interested, I'll go back to that particular document and try to explain on this particular concurrent technology. So for time being, excuse me, this is what I just wanted to let you know about the three options. But where we were at this thing. This was the just first solution we tried to address. Hope you appreciate now. What are the ways to reduce power consumption? The 10-15 minutes we have just talked about the circuit and processor level optimization for low power IoT. The second option is software and programs for processor. Let's say you are some coding engineer, you like to do the codes. How do you contribute for low power IoT networks? The first solution, you can reduce the number of lines of your code. The lower the program lines are there, the lower will be the power requirement, lower will be the time to execute that particular program. And for more and more time, your device can go into the sleep mode. That is what the second solution one can offer. Quickly, I'll go through other aspects also. Cloud server. So there are certain clouds. If we have a higher the traffic, higher power consumption would be there. So low traffic on cloud makes the data transfer easy, and that will reduces the power consumption. That is what the meaning. To have that, we have particular techniques called as OLTs and ONUs that will reduce the power consumption on cloud. And the last solution related to the communication protocols or schemes. So some of the communication protocols wherein, let's say you are using IPv6 LoRaWAN protocol, it will consume the less amount of power. Moreover, you can go with the SELPC, which is the communication kind of a scheme which reduces the power consumption for your communication protocol. So these are, I'm not saying these are all the solutions. This is what I understand from my kind of a study and some time I have devoted to understand how do I go for a low power IoT networks. So these are some of the solutions. There may be many more solutions or options available. I'm not saying that these are the only things, but right from circuit perspective, to the cloud, to the programming, even your communication protocol, and some of the advanced schemes being used in these communication protocols are going to help out us to reduce the power consumption and design the low power IoT networks. So this part we have already covered. So I'll directly jump to the next picture, which is here. Some power consumption. I'll take you to this data sheet of MT7681. I'm running very short of a time, so I'll try to cover the maximum portion which I have actually planned, because I think instead of just running the slides, it is more useful if I take you to some of the resources which you can further explore and get more and more idea on that. I'll directly go to this power consumption characteristics. Okay, you can see the current consumption in sleep mode, active mode, power saving listen, all these things in transmitter mode, in receiver mode, you can see it is there. So in terms of milliamperes, everything is being given. So this data sheet, it is from MediaTek. Whole lot of data sheet you can explore from the internet. So this is just an example of WLAN 2.4 gigahertz of current consumption. This snapshot I took for this particular data sheet IoT device. Okay. let me go to now the most interesting part of today's discussion. Rather last but one interesting. The interesting one is already over. Otherwise, you will scold me, sir. Every time you are saying interesting, interesting. Now this is the last but one interesting part. You can see the different devices and their power consumption in different modes and their release date. So this is from TI product, Texas Instruments. This is MT7681. I just showed you. So their power consumption in transmitter mode and slip mode is being given. Okay, so this is again we have already discussed. So please excuse me to not to discuss more on this, but just in terms of percentage, if you move from active to deep sleep and deep sleep to complete sleep kind of a mode, the amount of power consumption is reduced is given in a percentage over here, which you can read it out. Okay, how do you design it? Which I was actually interested to discuss. How do you design a power consumption can be obtained? So there is a formula. As we know, the device can be there in active mode for some time and it can be in a sleep mode for some time. Longer the sleep time, more will be the power consumption. You can say means lesser will be the power consumption. You can save on more on the power. That is what I mean here. Let's say you have two modes. One is the sleep mode. There is specific time of the sleep and you have some current consumption in sleep mode. That is why I have showed you this particular picture. Sleep mode, what is current consumption? You can notice it is 1.1 milliampere. And if it is an active mode, receive active mode, what is the power consumption? So there is a huge difference. 150 times almost more power would be consumed if the device is in active mode. Okay, so that is how you can consider how long your device is in a sleep mode and what is the amount of power consumed. So this is what nothing but power consumed, V into I. This is power consumed in sleep mode and V into I active. This is the power consumed in active mode. How long device will be in active mode and how long device will be in a sleep mode. Then based on that time, you can do a simple mathematics and come up with the average power consumption. So we are just considering two modes. You can even consider the different modes, deep sleep mode and so on and so forth. But I just wanted to make it as simple as possible. So I consider two modes of operation. One is the sleep, other one is active. Now this is the formula which you can use it to optimize your IoT network, and we'll do certain cases as I committed at the start of this session. So T sleep, if it goes to infinity, it means that your device is in a sleep mode for a longer infinite time. So your average power equals to the current consumed in deep sleep mode multiplied by the voltage, which is a P sleep. So this is what I mean. If this T sleep is infinity, above equation, the same equation will becomes V into I sleep. That is what your power in a sleep mode. Okay. So now equation 1 can be used and it can be used to derive the T sleep. So I'm not going to tell you because this is a very simple mathematics. You can use the same equation, rearrange it and write down for a sleep time. From equation 1 only, you just rearrange the terms from left hand and right hand side and come up with the sleep time. So values of I active and I sleep, this can be obtained from the device datasheet, which I have shown you. I don't want to show it again, right? Or you can do your own experimentations and you can come up with the current consumption based on your applied voltage. What is the amount of current being consumed that you can calculate in two different modes, I active and I sleep. And based on that, you can go ahead and calculate the T sleep. But here are two unknowns. What are the two unknowns? Can somebody chat it? Sorry, I will not take any chats because I am running very short of a time. So first unknown is a T sleep. First unknown is a T sleep. And second unknown is average power. So how do you solve this equation? You will have I active, you will have I sleep, you have these voltages, and you have the active time. So you have to decide what is the time slip for my device. And how do you decide that time slip? You will decide it from what is the amount of power consumption you are looking for. So I'll explain this with the particular example so that it will be very apparent to all of us. So we have to decide the slip time based on power consumption. So the value of T slip is unknown and the purpose of the formula is to get the value of T slip only. So the programming processors in IoT based systems, whatever you program in that code itself, you will write a line for how longer your device should be in a sleep mode that has to be specified. So T sleep can be calculated according to the required power consumption. That is what I said. Let me take one example. Let's assume I'll take 5 minutes to explain this. That is the most important aspect. Let's assume following parameters from data sheet or experimental observations. You have come up with these values. Your bias voltage is 5 volt. Device is in active mode for 30 seconds and it is consuming the current of 4.875 milliamperes in active mode, and current consumption in sleep mode is 0.01 milliamperes. So T active for node MCU, if you take, let us say 30 seconds, we have considered. This is what we have considered here. So the module program is written with a 20 seconds of a delay. So 20-second delay has to be there, and additional time to connect to the network, if you consider, that is what we have taken 30 seconds of a time for the node MCU module. So if you put these values and solve for T sleep, which we have discussed on earlier slide, so you come up with this equation 731.25 minus 30 average power, in denominator average power minus 0.05. So if you, let's say V into I sleep, it becomes 0.05 kind of a thing. So you have to solve this equation only I have used and I have come up with the T sleep. So if you solve this particular equation, you will get the sleep time. But how do you solve? You have to put the average power consumption. Then and then only you will solve this. So to know it, the last section of this case study is that, let's say you have been asked to design an IoT network or IoT system which consumes the 5 milliwatt of power. And other day, you have been asked to design the same system with 10 milliwatt of a power consumption. So you have two options. One is a 5 milliwatt power consumption, same system, nothing you are going to change. Your hardware is same, communication protocol is same, everything is same. Just you are changing the number of power consumption. One day you have been designing it for 5 milliwatt, other day you have been designing it for 10 milliwatt. The specifications are given already on the previous slide. And if you put the P average in this particular equation, so T sleep number will be different. Can somebody quickly answer this if possible? So if you put the average value 5 milliwatt and solve this equation, T sleep will be something. And if you put the value of 10 milliwatt, you can calculate the T sleep. I'll not go beyond my specified time. If anything is there, if you can allow me some 10-15 minutes more of time, I will be more than happy to discuss, because a lot of topics are remaining, but at least I'll cover this one and then we can go to the coordinator and take a call. So if you put the value of average power 5 milliwatt, your T sleep will become 117 almost seconds. And if you take a 10 milliwatt of a power consumption, your T sleep can be 43 seconds. So based on that, you can, based on your power consumption, you can take a call, you can write a code in a program, in the line in a program, and you can ask your device to sleep for a particular amount of time so that your power consumption can be optimized. I hope this makes some sense. I tried to cover this particular case study. Yeah, I have been requesting all participants, because I have given a T sleep. Now you can do a reverse way. You can go back to this earlier equation. The first equation, equation number 1. Now you have the, sorry, this is fourth one. The one, you have the T sleep, you have V and I sleep. You can put these values also already given, and you can compute for average power consumption. You will get the same number, 5 milliwatt and 10 milliwatt. This is the simple thing which I just wanted to discuss with you. Okay, so let me go to the coordinator, take a pause of 10 seconds. If anyways there is a possibility, I can go to the particular case studies. Otherwise, we can go for questions. Pankade sir, what is your opinion? Pankade sir, are you there? His team, somebody from Pankade sir's organizing committees, could you please confirm? Because I already touched my specified time. Should I continue, or can we take certain few questions and then conclude the session?
Ratnabargi sir.
Yes, sir. Yes.
Yes, please continue.
Hello. Sir, I'm not getting your voice, sir. Could you please confirm one more time?
Yes, sir, your voice is audible. Please.
Yeah, what do you think? Should I continue? Because I have almost at the middle of my presentation, there are too many topics to be discussed.
Just a minute.
Yeah.
Yes, sir, just let me check.
Yeah,
The next
because
session
other
is what?
speakers should not get affected. That is what my concern.
Yes. Just to give me.
We can take couple of questions or some discussion with the audience. And if anyways we have some 10 minutes of a time, please let me know. I'll continue.
Sir, you please continue. I'm getting in touch with the next session expert.
Okay.
Once they will join, we'll wait for the 5 minutes and then we'll end the session.
All right. Yeah, got it. See, so I'll try to just touch on certain slides wherein I just wanted to let you know. If any means I'll get some more time, I'll come back to my earlier slides, I mean, and show you the role of this UAV and role of sensors in precision farming. But for time being, let me take you to this particular slide, some of the case studies for automated irrigation. This is what the topic of our FDP, precision farming. So one topic out of that I have been selected, and this is what the IEEE publication which I found, which has been proposed this architecture for automated irrigation using GPRS module. I can't say it is a low power because it is always based on the designer requirement. What amount of power you will call as a low power? Whether it is a microwatt, you will call as a low power, or whether it is a nanowatt, you will call it as a low power. So don't go into that kind of a debate and try to understand the automated irrigation using GPRS module. So this WIU, wireless information unit, and wireless sensor units being used. So there are multiple wireless sensor units will be connected to the wireless information unit, and they all will be connected to the internet through GPRS network. And through internet, web server database is there, or your remote access with the different apps being designed can be used. So quickly I'll go through these details. So this is the WSO, wireless sensor unit. So it has got PCB, the radio modem ZigBee, and different sensors. As you can see, this C is actually a temperature sensor. This D is a moisture sensor. Okay. Similarly, different sensors can be attached to this, and this will it will make a wireless sensor unit. So WIU, wireless information unit, will have a master microcontroller, different isolators, memory is there, and it will be connected. This will be the only one. WIU will be only one unit in your IoT network, but there will be multiple WSUs, which will be going to collect the data from different locations in the farm and going to send it to the WIU. So this is what the system. So internal real-time clock and calendar will be there, which will set this thing. I will not go into the further details of this at the as the time sec. I can come back at any point of a time, but let me give you the broader picture of this particular project. So this is another view of the WIU with a radio modem and ZigBee as well as GPS, SIM card, and since we have been using a cellular technology, GPRS, we have to use the SIM card, which is being inserted at this particular. This is a GPRS module, and card is being inserted at this particular location. All right, so this is control. Then as I was saying during my yesterday's talk, I'll give you some idea on the sensors and controllers. I tried my level best to take you to the Quaro, to the slim radio concept, to the backscatter Wi-Fi. Moreover, I have covered some of the microcontrollers. PIC is the generally used microcontroller, but you can get more idea on this from our coordinator, Vankade sir. He has explored this area in wonderful way. So you can get more information on that. But related to this particular project, they have used this microcontroller, these different sensors, and these are the batteries. Even all the minute details they have been given. These are the components for wireless sensor units. There are multiple WSUs. Again and again, I'm trying to tell you, and WIU is the only one for which the same microcontroller is being used, right? So this is what the actual picture. These are the different, you can say, the beds A, B, C. At the different beds, different WSUs are being installed. Wireless sensor units have been installed, and they all are being connected to the central WIU, and they are sending the data related to the temperature, moisture, water over the time period. At the same time, every day, let's say at the 3rd June, this is what the data. For 4th June, 5th June, what is the data? For different beds, different wireless sensor unit or different beds, that is 54, 55, 56 and 57. So based on this information, you can control the water irrigation. Based on the temperature of the particular bed, you can control the water flow based on the moisture and water flow. As you can see, for every date and time, it is being given what is the level of water. Okay, so this is what one case study. So there is another case study also related to this cloud-based IoT. There also I have given a lot of parameters, but how these wind speed and rainfall in inches can be captured, and related to that, all these sensor, wind speed sensor and rain sensor, these can be used, and based on that, you can control your farming. That is what the precision farming. So humidity, temperature can also be captured. So for timing, I'll take a pause and I'll just try to get connected one more time with the audiences. If they have any questions, because I'm right at this 7:30. So if Wankhede sir confirms that, we can take a couple of questions and move on to the next session. That is up to coordinators now.
Yes, sir. We will take one or two questions.
Yeah,
I
yeah,
request the participant, if you have any questions regarding the today's session, they can ask the expert. Okay, yeah, I have given the right to all the participants so that they can unmute themselves.
Good evening, sir.
Yeah. Good evening. Please go.
Regarding yesterday's question,
Hmm.
so I had asked about how to incorporate these IoT sensors for rice yield predictions.
Yeah.
So this is if the sensors what we are going to purchase and install
Hmm.
and take the readings, real-time readings from the field,
Hmm.
how can I validate telling that those readings are correct?
Yeah, there is always uncertainty in the data. You have to
Yes.
see, as you have seen from this picture, there
Yes,
are
sir.
different sensor beds being installed. Yeah, this one. Similarly,
Yes.
based on that, you can get the multiple data from multiple sensors, and you can come to a common prediction. Otherwise, there is no any particular reference.
Oh, yes, sir.
There would be data uncertainty. Yeah.
Yes. So can we use sensors and collect the data for our research work?
Yeah, always you can.
Okay, sir. Thank you.
But you have to prove it somehow.
Prove it. Yeah.
You are doing certain research and proposing something.
Yes,
So
sir.
my sincere request is that at the end of your research work, you have to compare something like this.
Okay, sir.
Not this usual picture. Let me go back and show you one slide. Yeah, something. Let's say this is your work.
Yes, sir.
You have to compare with the contemporary kind of a technology. Let's say state-of-the-art low power communications. So these people have compared this thing, their work, with the other options.
Okay, sir. Thank you.
Yeah, thank you.
Okay, is there any more question? Okay. So I think Dr. Ratnabaki, we do not have any questions from the participants.
Yeah.
If there are any questions,
Wankhede, sir.
yes, sir.
Hello, I am audible?
Yes,
Yeah,
sir, you
yes,
are
sir.
audible, sir.
Yeah, Dr. Ratnaparki, sir.
Yes, sir. Yes, sir.
Thank you very much, sir, for accepting our invitation. And from yesterday, we are listening.
Thank
You
you.
are spare your valuable time.
Thank you.
And
Thank
we
you,
have
sir.
gone through the very thoroughly to each
Yeah.
and every slide.
Yes, yes.
Thank you very much from our family, CSMSS family, our management. You have given your valuable time. Thank you, sir. Thank you very much.
Thank you so much for your kind words, sir. First of all, I appreciate Wankhede sir, his team, and
Yes.
your entire CSMSS family for organizing this particular FDP and giving me a chance to spare some of time in this particular program. I wholeheartedly accept that I am not an IoT expert. To be very honest to all the audiences, they might have witnessed that I am the person from RF background. But see, IoT and RF goes hand in hand. That is what
Yes.
Wankhede sir and Ratna Parki sir always goes hand in hand. So
Yeah.
I tried to cover most of the aspects of IoT from RF perspective. And today I have shown couple of literatures wherein link budget and all these things are very much important to use for a IoT engineer. Thank you so much for your
Yes.
consideration for me as a speaker for this event. Thank you so much.
Thank you,
Yes,
sir.
sir.
Thank
As
you.
concerned to design and delivering the things for particularly low power devices which are
Hmm.
applicable for the agriculture aspect. Some
Hmm.
of the devices are very important for design point of view, and you have given your 100% for that. Thank you,
Thank you.
sir. Thank you very much.
Thank you so much, sir. Thank you.
Okay. So
Wankhede, sir.
now, yes, sir. So thank you, sir. We'll move ahead with the next session. Our next speaker is already joining the meeting. Okay, so we'll start with the next session. Our today's next session is on AI-driven computer vision techniques for precision and digital agriculture in smart farming practices. And our today's session expert is Dr. Papu Kumar Yadav. He is presently assistant professor in Department of Agriculture and Biosystems Engineering, South Dakota State University, Brookings, USA. Let me just give a brief about him. He has completed his BTech from SRM Institute and then MS in Electrical Engineering from California State University. He is the PhD in Biological and Agriculture Engineering from Texas A&M University. He is presently working as an assistant professor of Precision Agriculture AI Engineering within the Department of Agriculture and Biosystems Engineering. Prior to this, he was a postdoctoral research associate in the Department of Agriculture and Biological Engineering at University of Florida, Gainesville. His current role comprises 80% research and 20% teaching. His academic responsibilities include Prac 304-304L electrical diagnostics for farm machinery and technology applications for precision agriculture. Dr. Yadav's research interest encompasses various aspects of precision agriculture with the focus on remote and proximal sensing, utilizing multispectral, hyperspectral, thermal, and fluorescence imaging, as well as the implementation of artificial intelligence, computer vision, and unscrewed aircraft system, that is UAS, and unscrewed ground vehicle, that is UGVs, and agriculture robotics. With a good and vast experience in agriculture research, I hope this session is going to help the participant for their research. So I request our today's expert to start with this session. Sir, please.
Yes, give me a second.
Okay.
Yeah, hello everyone. Thank you for inviting me and providing some insight about AI and precision agriculture for smart farming practices. I hope I am audible.
Yeah, you are audible,
Please,
but I think just stop your screen. Yeah.
Yes, I believe now we are good. We should be good now.
Yes, sir. It is now good. Your voice is clear, video is clear, and the presentation is also clear. You can go on.
Yes, so today I'm going to be presenting about artificial intelligence driven or AI driven computer vision techniques for precision and digital agriculture in smart farming practices. So there will be a few slides quite similar to what I have recently presented. But these are very important slides, so I'll just walk you through again to provide you some insights on why there is a necessary for all the advancing technologies and why there is a requirement to adopt to all these new technologies in farming practices. So this particular slide that you are seeing, it shows that from the past how the population of the global population or the world population has increased and how much pressure it has put over the period of time on each farmer to feed them. So as you can see in the 1900s to the early 1930s, when farm mechanization was just happening, each individual farmer had to feed 226 people on an average in the entire world. Whereas when in the 1960s green revolution happened, so the yield or per acreage basis, um, it increased significantly during the green revolution through the breeding program and other practices. So you can see how the yield when it increased now, but the population also significantly increased. So when the population in the billions had crossed 6 billion mark, then each individual farmer, there was a pressure on each individual farmer to feed 155 people. Similarly, it is projected that by the 2050s, when the global population will hit the 9.6 billion mark or approximately more than 9.5 billion, then each individual farmer on an average will have to feed 260 people. So this is like a tremendous amount of pressure on each individual farmer. Now, why this is putting? Because the resources are limited. We cannot linearly increase the yield capacity as automatically, right? So it's not going to happen by itself. So what this basically tells that there is a need that we need to keep increasing our per hectare or per acre based yield capacity or production capacity to feed this increasing or growing amount of people. So how do we do that? So those are the things we need to we are going to learn from today's presentation. So let's go through the brief history of some agricultural practices. So as you can see in the initial time, like the traditional farming practices applied uniform application of inputs across the entire field. So you just apply some fertilizer, any kind of like water irrigation, you just flood irrigate, or you just apply any kind of nutrient input at the same rate in the entire field. That is what the historical practices has been. And even in terms of data utilization, we did not have a lot of technology, so we had very limited historical data knowledge, like how your farm does. Each individual farm is different. The soil texture is different. The microclimatic conditions within that farm might be very different. So what I'm trying to say is that if we do not keep collecting data for that particular farm, like historical data, then we do not know exactly how to manage that farm properly. So we had very limited data in the past time. Similarly, environmental impact, we really did not care about how much fertilizer we are putting in. We just applied whatever it was meant to be. We just randomly applied without properly doing analysis of the particular farm. And based on that, we did not adopt like precision farming practices. That is the reason why. So you can see even for the yield prediction, like my grandfather did this kind, they knew that they have been farming, they know exactly this much yield on an per acre basis or per hectare basis I'm getting. Probably I'll get the same amount of yield. That is how they practice, right? So these are just, I won't go much in detail, but just trying to show you according to all of these aspects, these were the traditional farming practices. One thing more I need to bring over here is either related to decision making was based primarily on intuition and experience over the past, or in terms of sustainability, very less sustainable because they did not practice, they did not much care about environmental impact of it. And again, harvesting timing was also very much manually determined based on visual observation. So these were, and of course, in terms of labor requirements, it was very labor intensive. No automation, farm automation was there. Primarily, they were done manually, manual labor force. So when we see these things, when we try to start adopting some precision agriculture farming practices along all of these approaches, you can see we start using variable rate technology application. Like exactly as I mentioned, each farm is different from another farm. Plus within the farm also there might be variability in the soil and microclimatic conditions. Even in a big large scale farm, which is let's say 100 hectares or 100 acres of farm, there can be a variability, microclimatic variability from one end of the farm to another end of the farm. So we have to take those factors into account to be able to precisely apply the inputs like fertilizer, irrigation, and also maybe they're based on their soil texture conditions, we have to adopt. So those kind of practices, they fall in the newer technology or the precision agriculture farming practice. So we use the new technology practices. They also include a lot of different advanced technologies. They make applications of GPS, sensors, drones, and IoT devices. In terms of input, it's like using the right amount without wasting a lot of chemicals or a lot of for different kind of chemicals. It can, besides fertilizers, it can also be pesticides. It can also be insecticides, those kind of chemical applications. So for yield prediction now, unlike like what we in the historical practices, we talked that they based on their historical experiences, they used to make prediction of their yield or based on visual observation. But now in precision agriculture, they try to use some data analytics tool, and based on their actually sensor based historical data collected, they make some prediction of their yield. So this makes actually more accurate yield predictions. Even for irrigation, it is more based on automated irrigation system using some sensing mechanisms, weather conditions data, those kind of things. And this becomes actually reduces the amount of input you are putting. It becomes more cost effective. At the same time, it uses a lot of automation technology, which we'll talk in the coming slides or the following slides. And for decision making, it's more data driven, and they make of application of some predictive algorithms. And this is how this basically you can again go through all the aspects and how they have improved by using this lot of new technologies to make better yield predictions, better resource utilization. So these kind of practices, when you are implementing, they basically they fall in the domain of precision agriculture farming practices. So what you are seeing in these pictures, all of these three pictures, they are basically showing some of the equipments that are used in the farm. For example, you have a robot here, which is an automated system. It's doing some spray application, and this is like precision spray application. And there is this drone, this is imaging. Similarly, satellite-based image data you can collect and you can map your farm, and you can do some data analytics to create some variable rate map or prescription mapping. Similarly, same kind of uh, information provided here. As you can see, there is a control system here. The user or a grower farmer, they can see the map of the field, they can get some drone data, and they can run some analytics algorithm on their computer. And they can do either they need to control the irrigation or fertilizer or irrigation applications, or see if there is some kind of a disease infestation happening in their farm. Another way to represent how different mechanisms, they are connected devices, they all are working in together, and they're all sending the data of the farm, different kind of data, either coming from this carriage, grain cart carriage truck, or different kind of tractors, which have different kind of sensors again. And and they are sending all the data in the central server, which is doing some analytics algorithm and providing some information or some informed decision making. So these are the things that how precision agriculture farming practices use. Similarly, what you are seeing in this particular picture here, it's an animated picture, but what it's trying to show is an auto steering system. So it's this tractor, or it can also be combined harvester, like either of it, like any kind of farm machinery, which can autonomously self-drive, go collect data or do some particular task and then come back, like without the need for actually manual or a human labor to drive this out. And actually, John Deere has, I think, they have released their fully autonomous self-driving tractors very recently. So I think it might get very more common in the coming days or years. Same thing here, as you can see. Again, combined harvester working together. Then there are other tractors collecting some other kind of information. Then there are some sensors actually installed, and this is satellite images. It can provide, you can basically the central server with a computing platform collecting data from all these farm equipments, including the satellite data, doing some analysis and providing all the informed decisions, whether for the driving, self-driving, autonomous tractors, harvesters, and then creating some maps. This is basically just I pulled out some data of this cornfield from 2013-14, and it's also provides some elevation data. So as you can see, as well as some bushels per acre. So based on these, you can find the regions where there are lower elevations. So it provides a 3D map, as well as it also provides here some average bushels per acre of the corn. So this yield predicted map. So you can find the regions where there are lower bushels per acre and when there are higher bushels per acre. So you can see the red zones are basically the lower bushels per acre, and the blue zones are the high yielding zones. So you can see like they are not very consistent with this. You can actually make your farming practices like why I am getting a higher yield in 2015 over here, and there are lower patches at the edges of this farm in the lower elevation over here, right? Is it happening because of some drainage happening right at this slope, or what is going on? So those kind of things you can analyze, like why you are getting higher, but you can see there is a consistent high yielding zone in this particular area. If you see here, these ones, but this area, even though in 2013 has a higher yield, you can clearly see it didn't have a very good yield in 2016. Now what happened? What went wrong? So those kind of analysis you can do. So how this, let's walk through like when this whole concept of precision agriculture evolved and how this is emerged. So it actually began with the early adoption of GPS technology in the farming practices, and probably that happened in the 80s, even though GPS technology existed way before that. But when it got commercialized and it started being adopted for commercial applications, it started being implemented on the farm equipments in the 80s. And then eventually you can see, as in the 90s, we started getting like this. It's hard in the harvesters. You can see they can actually, when they are harvesting and they are following this path, they can actually measure how many bushels per acre of, or whatever the yield you are getting as in real time almost, and you can record those data in your machinery system. And it can also basically apply some variable rate technology, like depending by creating some maps. So these all happened, started being implemented in the 90s. Now in the early 2000s, or in the 2000s, you can some UAVs based system started coming into farming agricultural practices. And eventually we are seeing from the late 2010s, the IoT, a lot of sensing devices being interconnected together, providing some informed data set, informed decisions. Yeah, this is being used nowadays in precision agriculture practices. And again, as we see, we are already seeing being adoption from the early 2020s, some automated robotic system, now robots and automated farming practices, either in this is an example of a controlled environment, like in a greenhouse settings, but these things are also being adopted in actual farm conditions also. So what exactly precision agriculture is? How do we define it? So it's a management strategy, as you can see, that uses information technologies to bring data from multiple sources to bear on decision associated with crop production. So this is how it is defined by a book that is titled Precision Agriculture in the 21st Century. So to make an informed decision by collecting data from multiple sources for um, management practices or efficient management practices. Sometimes it is also called site-specific farming practices. And the whole objective is to increase crop productivity by decreasing the production cost and minimizing environmental impacts. So the term precision agriculture was first coined in the 80s by Dr. Pierre C. Robert, and he was a faculty professor at the University of Minnesota and he started the world's first precision agriculture center at this particular university in 95. So sometimes he's also called as the father of precision agriculture. So when we talk about precision agriculture, we are talking about 4 R's. These are like right source, right rate, right place, and right time. I won't go much in detail, but this basically means, are you applying the right source? Means, are you ensuring that the input that you are applying it should be pesticides, or it should be herbicides, or what exactly it needs to be there? But how much, at what rate you need to apply, and at what place you need to apply, and at what timing. Timing is also very important. So this is exactly the 4R concept that precision agriculture technology uses. Now, how does it? So I can see a raised hand by Praveen Turare. Yes, Praveen, how can I help you? You have a question?
Hello. Yes, sir.
Yes. What is your question? I'm sorry, I cannot hear you properly.
Yeah. Praveen Turare, sir, do you want to ask any question?
Okay, so the steps that are involved in the precision agriculture, as you can see, from data collection to data analysis to decision making, and then how do we implement it by variable rate application or robotics and automation technology or precision planters. And then we monitor, continuously taking feedback to keep improving, right? Because the ultimate goal is, can we improve the yield, or can we make it more cost effective? How can we generate more ROI in terms of return on your investments, and at the same time also practicing the sustainable agriculture practices without damaging the environmental aspect of it. So those kind of things. So how do we know that? By continuously monitoring and getting feedback and making adjustment of all the system, this entire farming practices. Like, so you are not only monitoring, you are taking the feedback, and then when you see some problem, or then you are going back and you are doing some adjustment. So it's like a loop and a cycle. So continuously you are adjusting your management practices so that you can have better yield, and you in a cost effective way, and at the same time without impacting or causing some negative impact on the environmental aspect of it. So the overall objectives, as you can see in the precision agriculture practices, is to increase profitability and sustainability, production efficiency, optimizing product quality, efficient use of farm inputs, soil conservation, water energy, and surface and groundwater protection, because we do not want to apply too much fertilizer and start contaminating. So environmental aspect is also important, and maintaining soil health is also very important without contaminating water or energy surface. I mean, this basically ties to this point, which is minimizing environmental impact and also minimizing some risk associated with it. So what kind of tools we can use? As I already told you, GPS is one of the commonly used tools in the precision agriculture practices. But at the same time, we have a bunch of sensors, like as I told, like remote sensing based sensors or proximal sensors. Now, what are remote sensing? They can be aerial based or they can be satellite based. By aerial based means drone based technology or satellite based technology. Then the sensors that are proximal, like in-field sensors or in-field crop sensors, they can also be inserted in the soil, like pH sensors, EC sensors, nitrate sensors, soil moisture sensors, those kind of sensors. Then the crop sensor, they can be chlorophyll meters, spectroradiometers, like handheld. You can see the chlorophyll meter here, how this is a proximal sensor. It measures the chlorophyll content of these leaves. And then with all these, you need basically some analysis tools like GIS, ArcGIS, everybody know, or Envy, or you can even do it in a programmatic. So basically, you need some analytic tools to analyze all the data that you are collecting and make you some informed decision and create some maps. Do you need to do some variable rate application? And for all of these things, you basically need some modeling approach. You can use AI models, you can use spatial decision support systems, or crop simulation models. So when you are collecting data, you do analysis using these modeling approaches, and then you make some informed decisions about how much input you need to apply or what you have to do, those kind of things. So these are all concepts that collectively, that's how you implement your precision agriculture technology. This is basically just the flow chart, just pretty much representing the very similar information. Now, when you see, we talk about some examples of precision agriculture application, let's talk about some yield mapping. So let's say you have some cornfield and then you map, collect, either you use satellite data or you use drone-based data. And you can also get some EC-based mapping, like electrical conductivity based map, by scanning your field. And then based on that, you can actually use some software tools and you can create this map, like which are the zones that will give you higher yield and which are the areas that will provide you lower yield. And you can basically have a map, and based on that, you can make some, okay, there might be some less yielding areas or there might be some higher yielding areas. So as you can see here, these are actually here the red zones are like higher yielding areas. You can see in more metric tons per hectare. These are the regions which are giving you higher yields compared to these ones, which has a lower yield. So this is how you create your yield map, just letting you know. This is just one example. Similarly, you can also use for disease mapping. Actually, you can see like a white mold is a common disease in soybean. And then you can see there are different corns and soybean, they have been mapped. At the same time, the occurrences of white mold disease, all the red patches that you see. So these are basically the regions where there is an occurrence of white mold disease. Now, how did they get this? They used some satellite images and they used some analytics tool, as I already told, and they created these different regions where there is a prevalence of this white mold disease. And you can see how they look like, the color changes of the leaves, those kind of things. Similarly, you can do for other diseases also, like corn leaf blight or any kind of diseases, like soybean SDS disease or corn tar spot disease. So just giving you example that how and what are the examples applications that you can use that. Now, how can this be useful in precision ag is that when you have these maps, you can basically just go and apply some pesticides related to control this particular disease in only these regions. That's what basically is trying to tell you. Now, for variable rate irrigation map also, as you can see, there is a pivot weight irrigation system here. As you can see, there are regions, you can see like how many percentage of water needs to be applied where, like what is the existing soil moisture. So these are like wet regions and there are some dry spots. How many based on that, how much inch of water you need to apply in each of these regions. As you can see, these yellow spots, so basically they are tied to these particular zones, and based on that, when your pivot moves, you can adjust your rate of irrigation for that particular zones. So you create different zones of irrigation. Similarly, now how do you do that? You can have some soil moisture in-field, in situ soil moisture sensors like installed here, randomly placed. And based on that, you collect data, you again use analytic software tool to interpolate those data and then create your map. And based on that, you can make how many inch of water you need to apply in that particular zones. Similarly, this is just another way of creating a variable irrigation map using some satellite-based data set. So I won't go much in detail. This will pull out from this particular paper. So anybody interested in more to go more in detail, as you can, please go ahead and use this. So basically, they created based on electrical conductivity map at different depths from 0 to 9 centimeter to 0 to 30 centimeter. That's what they did. So EC is electrical conductivity. Based on that, also you can actually primarily all of the soil moisture sensors, to my knowledge, when they are working, a lot of them at least I can say, they first measure electrical conductivity present in the soil, and then using some equations, they convert that electrical conductivity into soil moisture data. So based on this, you can make your decision how dry or how wet your soils are, and you can adjust your irrigation application based on that information. So similarly, you can do for your fertilizer applications, as you can create different maps for variable rate nitrogen applications, like how many kilograms of nitrogen per hectare you need to apply in different zones. And as you can see, based on that, you can see how much yield you can expect to get in each of these zones. So what are the emerging precision agriculture technologies? You can see that in the remote sensing platform, drones, ground-based robots are like emerging technologies, and also quite being already used actually. In ground sensors, there are different kind of ground sensors. They are emerging like temperature, moisture sensors, nutrient sensors. They provide farmers almost like a real-time data to do some adjustments. Targeted spray application like precision spray applications, it uses some AI or machine learning tools to precisely spray at a specific spot. Automated mechanical weeders. This is another like mechanical weeding system. Again, uses AI. It's like almost like a robot, or whenever we talk about automated systems, and it uses for this is also one of the emerging technology in the precision agriculture domain. So let's see how they might look like. As you can see in the greenhouse settings. So here is a robot. As you can see, it goes automatically. It inspects your crop. And if it requires, it has some disease, then it might adjust its inputs by applying some fertilizer. You can, or if it is dry, you can also actually spray, and you can apply irrigation either using through this, but primarily this is used to do precision application if there is some disease infestation, or if it requires some fertilizer applications. So in controlled greenhouse setting, you can implement this, but how do we do this in the large farm scale? So as you can see, this kind of spray application systems, when it is spraying, it's also actually spraying not only fertilizer, it can also apply your pesticides. This is the spray boom system mounted behind a tractor. And then John Deere has developed the see and spray technology. So when there are some weeds also, it can precisely just spray at the weeds. But right now, it can also do some precision fertilizer or precision pesticides or precision herbicide applications. I have already talked about this automated farming, steering, self-driving tractors. Similarly, in the greenhouse settings, they can also do mechanized harvesting or automated harvesting systems. So they can inspect, and they have some robotic manipulators with some end effectors and different kind of end effectors. If it is a tomato, you might want to have different. If it is a chili pepper, you might want to have a different kind of end effectors to basically harvest those crops. So automated harvesters are also being used. Similarly, drone-based spray technology, we are pretty much, whoever have some knowledge about precision agriculture, they might have already seen this. From crop inspection to some spray applications, it's commonly used. So we already know now what exactly precision agriculture is, and now let's talk what exactly AI is. So I don't think like any one of us here haven't heard the term AI. I mean, it's been there. So it basically refers to the simulation of human intelligence in machines that are programmed to think, reason, and learn just like we humans do. Now it's a broader term, AI. It's a broader. A lot of people we confuse or they interchangeably use deep learning, machine learning, and AI. But basically, AI is a broader field within which to implement or make a machine intelligent, we use some learning algorithms like machine learning algorithms. And within that, deep learning has become quite popular in the recent days, I think since 2012 or something like that. And then this is basically a subset of machine learning, and overall it's a subset of AI. So the key components in AI are the learning algorithms. As you can see, machine learning algorithms. It helps to make some informed decision or learn some patterns in the data that you are getting from your farms, and also new natural language NLP. But to understand the human language, you can tell your robots or your tractors to the farm machine to go and do some tasks. They can basically understand. They can get the command from purely from human language, and your robot can go and, let's say, harvest your tomato or those kind of things. And automatic physical tasks, again, robots are complete. These are the key, primarily being used in the domain of AI and the computer vision techniques. Now, today's talk is more focused on the computer vision aspect. So how AI can drive the computer vision tasks. Now, when we talk about computer vision, is understanding the visual inputs, or like we humans, when we see something, we can recognize whether it's a apple, whether it's an orange. So how do we make that decision? So we can your robots or your machines to actually understand what crop it is, or and based on that, what task it needs to do. So this is where our today's talk is more focused, and how we can use in precision ag and digital agriculture practices. So let's go one by one. So what are AI computer vision and AI driven computer vision? So while AI is a broader field, as we already talked, focus on creating machines that can actually mimic the human intelligence. So machine learning, which is a subset of AI, focuses on building models that learn from data. So it's like a mathematical framework, machine learning. It how it can recognize some patterns from your data. So just giving a random data doesn't make any sense. You need to provide some mathematical framework so that your machines can understand what that data means and how it is supposed to be used. So as you can see here, AI is a component that combines the overall component and makes robot to sense, like we humans can touch, feel, and then perceive something using some visual information, and then navigate. For example, this robot, it's actually using AI to sense, so it knows exactly it has to keep driving straight because it has some visual sensors and it is having some perception, and it can do some autonomous task. If it has to spray, or it has to collect some data, or it has to do some mechanical or some weeding by using some actuators or mechanical systems. So how does it do all those tasks? By using some components of the AI. What are the components? Sensing, to perception sensors, and to also use some navigation, doing all these tasks autonomously. So these robot actually, how does it make decision just by collecting the data? It uses some machine learning algorithm. And then if it is a robot that is doing a task for disease control, then it can do some crop disease detection using some visual sensors. Or if it is doing related to predict yield, so it can collect the EC data from the soil, or it can collect some your corn data, create some NDVI or some indices from the canopy of this corn with a very high resolution, and it can create the map. It can run through the entire field, and you can actually merge all the information and create a more high resolution map compared to what you get from the satellite or drone. So those kind of things it can do. And the algorithms, there are a lot of different algorithms. I won't go much in detail, but there can be a totally separate class for this: random forest, linear regression, support vector machine. These are very traditional machine learning. In the newer, if you remember this previous slide, I said deep learning is a subset of machine learning. So within the deep learning, if you see, sir, excuse me, there is a component called neural networks. And within the neural network, something called convolutional neural network, which has got very popular. And this aspect of deep learning, which is a subset of machine learning, is quite popular in achieving all of these tasks. So let me ask all of you, can you think of when was the AI first used? Because it looks like it has got a traction recently, and we might be thinking, oh, it's a very new thing. But guess what? It's not very new thing. The term AI was first coined by John McCarthy in the 1956. So this term has been actually used from the mid 50s. So it's not a new term. Similarly, the term machine learning was coined by Arthur Samuel in the 1959. So for us, it might look like, oh, we are all talking about AI and machine learning. Must be very new concept. It's actually not. These terms have been used from the 50s already. So then there was some rise, and eventually no progress happened because we didn't have enough computation or not even well advanced algorithms. Then from 2006 and 7, again, the computing capacity started with the emergence of GPU technology and stuff. Then we started, and from 2012, there was a whole range since the introduction of algorithmic in terms of progress of different kinds of algorithms in AI, starting from AlexNet actually in 2012. So that's how it actually started. But the term has been this whole concept, this has been into existence for quite a long time. About precision ag, we talked about AI, different algorithms of AI. Now let's talk about what this whole computer vision technique is all about. So computer vision is also a field of AI that enables machines to interpret and make decisions based on visual data, such as images and videos. So you can see here there is an apple orchard. We human beings, when we are looking at this, we can tell it's an apple because of the way our brain has been trained to recognize. But let's say if there is a child or a kid, if you ask a kid who very likes a 1-year-old kid or 2-year-old kid who has not been trained, probably that kid would not be able to tell if it is apple or it is a strawberry, right? So we train the kid and he starts seeing some patterns, either in terms of color perception or the shape, feature, textural, this information. And over the period of time, the kid learns that no, this if something looks round and reddish color, this kind of shape, then it should be an apple. And if something looks like this, then it should be a strawberry. This is exactly what computer vision makes the machine to recognize. So if you have a robotic harvester that needs to harvest apple, it first needs to recognize that this fruit on the tree is apple, and then it needs to find the location and then move its manipulator or with the end effector and then do the harvesting application. So this whole approach is called these computer vision tasks because it's visually trying to recognize the information or the type of fruits on the crop. Similar thing if you have an strawberry harvester, same thing. First, your robot, your machine, it needs to first, using computer vision and AI techniques, it needs to first identify if it's a strawberry or not, and then how far the strawberry is, and then make the decision and with how much force it needs to apply to harvest it. So those are the key components. That's what basically means. So how does this whole gets thing the whole process of computer vision technique applies, implemented. So you acquire an image using some visual sensor. So you have some camera. It can be multispectral or RGB or hyperspectral camera. From that camera, you do some filtering. So these are like some basic noise cancellation, image processing techniques in the background noise clearance. And then eventually you extract features, which I was telling, edges, shapes, colors. So these are the features. And then based on that, you interpret whether it's an apple or whether it's a strawberry. And then you try to achieve your tasks. So we know what computer vision is. Now, what is AI-based computer vision or what is AI-driven computer vision? So as I said, when we are talking about shapes, edges, and features, in the past, they were being done using some traditional image processing techniques. Now, those techniques, they were not implementing the AI algorithm. So you can achieve a computer vision task from traditional based method. And at the same time, you can use the computer vision also by using some AI algorithm. So when we talk about AI-driven computer vision, it basically means to achieve a computer vision task, which is like object detection or classification task, not using the traditional machine and traditional image processing technique like filtering and all those things, but you are using some AI-based algorithm that can automatically tell whether this is an apple or this is a strawberry or this is a corn plant or this is a weed or this is a sheep, like that. So what you are seeing in this image, as this robot is moving or this drone is flying, you can imagine any kind of farm machinery equipment. As it's moving over the top of canopy, it's creating boxes by analyzing, by detecting these corn plants, and it's creating a box around it. You can create, let's say, an app on your phone with just based on the camera, RGB camera of the phone. This with the AI technology, it can tell the what disease is present on the leaf of this corn. Similarly, you can use AI in the animal industry also, like it can actually count the sheep when they are moving. If you have a camera mounted and it tells, it is trained with AI to detect the sheep, then it can also do counting, and you can imagine, so it can keep the track of if you are lost any sheep in your let's say in your ranch. So those kind of not only sheep, it can be applied to any kind of animal counting like chicken in the poultry industry or out of the beef industry or the cow industry or any kind of animal based practices. So this is another way, another approach of like AI driven computer vision. As you can see, you are flying your drones and it's creating the maps, and at the same time it can create different layers, different kind of indices basically, and it can tell you if the crops are need some fertilizer or they have some disease infestation, so they might need to be treated using some insecticides or pesticides, or how much even water is needed. So those kind of things, you can create the map. Now, when we talk about smart farming, so we talked about AI, we talked about AI-driven computer vision. So AI-driven computer vision can be implemented to achieve the whole goal of smart farming practices. So in the smart farming practices, you can see these are the different components that are involved. So you start with the smart devices or the physical layer in which you have your farm where you have a lot of equipments like drone flying, satellite data. You can also collect data using some farm machinery equipment. So when you collect all of these data using a tools and techniques, you need some communication network and you transmit it to your processing, like some central server. And then from there, you can either push the data on the cloud and then do some computation over there for your decision making, or you run your algorithm there, or you can also do in the edge itself. By edge means basically you can have your computer right on the tractor or your farm equipment to make the decision right there, or you can also have the option to push it in the cloud. The cloud will make some decisions, send back the maps or informed decision to your farm machinery to do some tasks. So this is how you can actually achieve the whole concept of smart farming practices. And it uses sensing technology, software applications, communication system, telematics, hardware and software systems, and data-driven solutions. When you combine all of these components, basically you are using some smart farming applications. So what I'm trying to say here is, when we talked about AI, we talked about AI-driven computer vision and precision agriculture or digital agriculture. We can actually combine those two and we can have a whole concept of smart farming practices. So let's see, when we talk about all this, how can these technologies in the context of India, how can they be implemented? So India is also, as you can see, it grows wide range or varieties of cropping system. It has from rice to corn to soybean. Then they also grow wheat, barley, mustard, peas. These are some of the major crops, as you can see, depending on the state wise. So in the southern states, you have again rice, coconut, spices. So all of these crops that we are seeing here, they also can actually benefit by all these AI-driven solutions, computer visions in smart farming, for smart farming or digital agriculture applications that we talked about, to increase the productivity of the farmers and on per acreage basis, and also to generate more ROI. So, in all of these crops, major crops that we talked in India, so there are different kind of challenges. As you can see, there can be challenges related to drought or challenges related to some disease. Sometimes you get too much heavy rain, sometimes you got drought related issues, sometimes you got pest infestation. So this kind of, I think in India, this is a major problem. We see that because they have not access to all these technological tools and advanced method, they cannot actually manage their farms, in a proper way. And then sometimes, a lot of the time, they just end up like incurring a humongous amount of loss, and they go under a lot of debt actually. So these are some of the challenges. As you can see, we have a very low level of mechanizations, which is like we don't have like automated mechanization machinery systems. Fragmented land holdings, it's like a small scale farming, and they're they're bits and pieces. They are not like at a larger scale or mid-size scale to implement all these technologies. Then there is, of course, drought related issues and not smart farming practices. So irrigation is, I think, still primarily carried out on the flood-based irrigation systems. So those kind of issues are there. Soil degradation, because farmers are not aware how to manage their soil health. So either they apply too much fertilizer, just they without actually being concerned that it actually can hinder the productivity over a period of time if you just over apply. At the same time, it also causes the groundwater pollution, because this over application can leach and contaminate the groundwater. So, and also because of this, when they evaporate, they actually generate a lot of greenhouse gases. So they have a climate related issue. So it's very important to implement farming, these kind of practices that we talked about for better agricultural practices. In rice, we have bacterial leaf blight kind of diseases. So issues related to disease are also another problem. And these problems are actually global problems. But when we talk in context of India, again, there are also rice related disease infestation. Then we have wheat related some disease like rust disease, we have kernel burnt disease, or then we have loose smut disease. These are also another diseases. And since wheat is major crop in India, it's important that these practices are implemented to control and manage the diseases properly. Similarly, in the corn, as where I am right now in South Dakota, corn is a major crop. In India also, corn is major crop. So there are diseases related to leaf blight, downy mildew, some of these diseases. And these diseases can also be managed properly or wisely by using all these AI-driven solutions that we talked about. So what kind of strategies? Either we adopt some disease resistance varieties through breeding program, like using genetic engineering, or integrated pest management by combining biological, chemical, and cultural practices. But since today's talk is based on the AI-driven aspect, we can use these AI-driven solutions for disease detection, and we can do some precision spray applications of fungicides and pesticides, those kind of things. So when we implement these, we can, as I told, there are some remote sensing techniques also, like satellite-based sensings. And I would, since due to time constraint, I think I would try to not take too much time. But as you can see, there are different kind of satellite-based sensors. They are with different spatial resolutions, and you can with different bands that can collect data in different spectra. And you can use them to get some thermal data or hyperspectral data or multispectral data. Similarly, you can use them for getting evapotranspiration information, basically how much to irrigate. So when we talked about drone and the in situ ground-based sensors, we can also use satellite-based sensors to create these kind of maps. I have already talked about the spatial analytics tools like GIS. So this is just showing an example how GIS software tool can be used to create the maps by using the satellite or the drone-based data. So this is like one of the CN spray technology. As you can see, you can do some real-time management aspect, or you can first create the map using some drones and satellites, and then upload it on your machinery system, as you can see on this spray boom system, and then you can do the management. So this is a conventional practice of precision, but this is like a real-time spray application. This is the modern practices of precision farming. And all of these are using actually AI-driven computer vision solutions. We have already talked about in situ proximal sensings, but I would just like to focus here the EC mapping that when I was talked about in the previous slide. This is the equipment that you basically mount and you can drive along your field, and it actually creates the map, and you can interpolate and create a EC map. And it is very useful information. You can predict the yield of your field and those kind of things. And these are another kind of sensors which we have already talked about. What kind of drone we can use? As you can see in drones, you can mount some of these multispectral cameras this is the Ag Eagle, MicaSense, RedSP, which is a very popular sensor. This is the Altum PT sensors that you can mount on your drone. It has also a thermal camera along with the panchromatic, so 5 bands. And what are the 5 bands? These are the 5 bands you can see here. They are basically RGB data besides red, green, and blue. You can also have actually red edge band, and then there is a near infrared band. And this can help you to generate these kind of indices like NDVI indices, NDRE indices, or color infrared. So these kind of maps you can create, and you can do some farm management practices. You can also use hyperspectral data. Again, these are just like takes more wavelengths. Besides just going through a visual spectrum, you can go through, let's say, for example, from visual. So these are the from 300 or 400 nanometer range to 750 nanometer range is almost like a visible. So it captures the red, green, and blue channels or BGR channels. And then beyond that is a near infrared channel. And then you can go to the some other wavelengths beyond that. So this information can be also useful in actually disease detection, because sometimes what happens visually, the corn or these soybean leaves, they may look very healthy, but when you actually start inspecting in the other spectra, then the disease can start showing up. So that's why it's important to use hyperspectral to actually see beyond our visual perception. Similarly, as again, you can use drones, you can mount all these cameras that I talked about, and you can create these kind of spatial maps to do your precision farm applications. In the modern remote sensing technique, as you can see, fly drone, you have the software that can tell you all the analysis. It can do the analysis for you very easily, and it can tell you which location region in the farm has some issues and what you can do. Now let's see how we use it. Overall, when we summarize this, we use it for crop monitoring, for disease monitoring, stress detection, yield estimation, soil moisture mapping or soil moisture detection, mapping of water resources, irrigation management, fertilizer. So as I told you, these are the key areas in which you can use, and beyond this also you can use for other applications. Again, 3D mapping, you can use some LiDAR-based sensors to find the elevation. If I apply some water, it might drain into one specific region and carry away all the nutrients and deposit in that particular region. So those kind of analysis or practice, farm management practices can be informative using this 3D map. You can also measure the height using some 3D modeling, like how tall your crops are, and based on that also you can say if your crops are behaving well, they are doing well or not. Then with all these systems, we have already talked about IoT systems, how these all things, sensors, they are interconnected and together with a central server, and they provide all this data. And you have some software to do some analysis to make your either irrigation decision or fertigation decision. This is for crop monitoring using some, as you can see, NPK sensors. And then you can also send the data directly to the edge computing device, either on the drone itself, or it can transmit the data to the central server through the IoT system, and then does some analysis and send it to a computer, or it can directly send to this computer and it can do some analysis right there. So there are different ways to do that. Similarly, you have some robots and some farm equipments. We have already talked about some doing some spray applications or some harvesting applications. very much similar thing what we talked about. But one thing I like to focus over here is in this robotic system that you are seeing, this basically it has some nitrogen probes that inserts in the stem of this corn plant, and it actually measures the sap flow in this stem. And based on that, it can actually measure the actual nitrogen flow happening inside the stem of this corn plant. So this is pretty cool actually. So yeah, thank you. And I'd like to thank Dr. Priti Sawai Ram, Dr. Gopal Sinde, Dr. R.G. Bhagyavant, Dr. Devendra L. Buyar, Dr. P.R. Wankhede, and to all the team of CSMSS group for inviting me to provide you some information. And here is my group, my lab group, all these wonderful people working with me. So thanks to them that some of the information or data I provided, they have worked hard so that I was able to present some of that here. Any questions I would be happy to take. And if you have any additional questions, you can email me always here. Thank you.
Yeah. So, thank you, sir. We'll take a few of the questions from the participants. Dear participants, I have given a right to unmute yourself. If you have any questions, you can ask the today's speaker.
So good
Yeah.
evening, sir.
Yeah.
Sir, am I audible?
Yes, ma'am, you are audible. Please go ahead.
Sir, this is regarding, I'm a research scholar. Right now, I want to work with rice yield predictions. So this I have thought like I have to include the soil parameters, the historic yield data, and then come with the yield predictions. So with this, I want to optimize the algorithms like LSTM. Already in the literature survey, most of the models are being already applied. So in this direction, what could be the suggestions?
Yeah,
Yeah.
that is a very good questions actually. So there is no one specific answer how to optimize your models. Now there are different aspects of it. So in order to optimize to make a better yield prediction, when you are talking about the LSTM, which is a time series based model, of course, you will need some historic weather data besides the historic yield data itself. And you might want to collect some, let's say, soil EC data, which you might have already. Did you collect, have you implemented the EC electrical conductivity data, if I may ask?
No, sir, not it.
Yeah, so the electrical so as I said that if you can map and create an EC data, that can provide you a very good input to the LSTM model, how it has changed over a period of time, even though it changes only very rarely over like from year to year basis, but definitely it can change over a period of time. Second thing I would recommend, and have you implemented the weather-based data in that model?
Not with LSTM, sir. I have tried with other algorithms like CNN.
Yeah, CNN, you tried weather data. Okay.
Yes.
So
Yes.
anyways, okay. So yeah, so those are the some directions you can look. And these are from the perspective of the kind of input that you can give to optimize your model. Now, this is based on the input side. Now, when you have the modeling, any AI algorithm or deep learning models, they are parametrics in nature. They have like hundreds and thousands and millions of parameters. So you can also try some optimizing by some fine tuning those parameters. So you can play with their hyperparameters that are tied to your LSTM model, and you can start trying to adjust those parametric values in those models. So that is one very important way that you can actually think about how to optimize those models. And of course, besides this, there can be other ways to refine and fine tune those models. I hope I was able to answer your question.
Yes, sir. Thank you.
Sure.
Yeah, any participant would like to ask a question?
Sir, I want to continue with the madam's question that she just asked. As you have said that we can try with different hyperparameters. So in that case, should we go for experimental basis or we should go for some algorithms? Like if we see in papers, there are so many optimization algorithm. Every researcher is proposing one or the other. So what is the best way if I want to do my research? Do it experimental evaluation or try to renew or modify some existing optimization algorithm?
Right. So again, there is no one right answer to this question. Since you are doing research, and as a researcher, we all know that we have to keep experimenting different ways. But as a starting point, from my experience, I would definitely tell you to whatever the data you already have, first try to optimize the hyperparameters. And there are different kind ways to do that. Like you can use genetic algorithm to optimize your hyperparameters. And there are other techniques you can explore how to optimize those hyperparameters. Once the hyperparameters are optimized and you are not seeing any improvement, then the only option you are left with to start feeding with some additional input data, right? Or more data. So that's the way to go.
Thank you, sir.
Yeah, sure.
Okay, is there any question from the participants?
So let me see in the chat box. I see, okay, if there is any question.
You can put your questions in the chat box also. So we can go through the questions and the expert can answer them. Sir, I just want to ask one question to you. As a
Yes, sir.
researcher, you are working with one of the international university. The undergraduate, how the role is there from the undergraduate and postgraduate students?
Sir, can you repeat once again about the undergraduate student? I'm a little bit.
Actually, I just want to know what is the role of undergraduate and the postgraduate students in the research that we are doing at agriculture?
Yes. So in my case, I have couple of undergraduate students working, and they can always help in field data collection and contribute to the research. Like, since they don't have a lot of research experience, the best way they can contribute is we can provide them or take their help in assisting some field data collection, for example, soil sampling, flying the drone, help and provide some coding related knowledge, take their help. If they are from different background, like computer science background, they can help us in trying to, let's say, train the model. If we just basically teach them some basics. So those kind of tasks definitely they can do. They can sometimes also contribute in creating some graphs or analyzing some of the data if they can be trained that direction. So they can always be helpful in terms of speeding up your research pipeline, workflow pipeline that you have. So that is one way that they can definitely contribute. The graduate students, definitely, they are the core of any kind of research program. I mean, yeah, if that answers your questions or there was anything additional. I think you are muted.
Yeah, that is the same. Another question is, now you are working at the in USA. how and now the Indian scenarios are very different. So how would you suggest to work around with such type of technologies?
Yeah, that's another very good question. Actually, that is a very important and interesting questions to understand. The most important factor to understand would be like in the United States here, we basically farm at a very large scale. Most of the farmers are large scale farmers. And that's why they can afford those big and heavy machinery systems, like big combine harvesters, big spray boom based systems, right? And since they have bigger budget, because they are farming almost like at a corporate levels, so they are able to either rent, or most of them they just own those big heavy machinery equipments. In terms of coming to perspective in the Indian scenario, first of all, the climatic conditions are different, the farming practices are different, and to understand the scale that they are farmed at a smaller scales, how can we adopt or create or optimize those machinery systems at for the in a cheaper and more cost effective way. Let's say, for example, can we design those combined harvester or make it a little bit smaller scale so that it is affordable? Or can we have a different business model in terms that those farmers, they can just rent it, just pay on a timely basis. If I'm renting you for like 5 hours, or I'm renting you for let's say 50 acres of my farm, or 30 hectares of my farm, I'll just pay you this much on an per hectare basis, and you just harvest my crops. Or you just fly your drone and just map my field and provide me some information that what I need to do, what if you can just provide me, or you can send your equipment to do this kind of task. So those kind of transition definitely needs to be understood uh, uh, from one country to another country basis. Yeah, but the basic techniques and algorithms that we talk, I don't think they are geographic. They are geographic agnostic. So what I mean by this is they can pretty much be implemented at any part of this world. The only thing is how can we scale it down, and how can it make it more cost effective way? Yeah.
Yeah. Another question is, what are the different applications that are shown for the computer vision? Uh, so whether we have to go through the readily available data sets, or we have to create our own data sets?
Good question. Good questions. I'm so glad that you asked these questions, because I think this is also tied to this question by Salini ma'am that she had asked earlier. So existing data would be definitely the starting point. We definitely need those existing data set to train the model in any kind of AI-based algorithm. But as I mentioned, to make it more better and accurate, better can be very generic term, but let's say in terms of to be able to predict with less amount of error, we definitely need our local data set also at a farm scale data set. So because the scenarios are very different, and the biggest challenge with any kind of AI model is that uh, they are not generalizable. That's their biggest challenge. By what I mean by that is that if I have a data set from Maharashtra, and if I want to, let's say, implement it in Bihar or in the West Bengal or in Haryana, that model may not work as per the expectation, because the soil condition is different. So it is reflecting to the sensor in a different way. Uh, the weather conditions might be different. So those conditions definitely can influence the predictive ability of these models. So that's why it's very highly recommended to fine tune those models. We need to collect some local data set, and then we need to refine it and tune it based on the local data set to perform or to do better predictive that is localized to that. Yes.
I move ahead to the last question. Nowadays, we have lots of different embedded boards are available in the market, with which actually most of the students or the researchers start their work. Just like we have Arduino, ESP32, and Raspberry Pi is around there. Would you suggest whether you have to go with such type of boards or you have to go with the high-end controllers or any embedded boards?
Yeah. So this is very subjective question, and it's very hard to tell one specific board over the other.
So,
But to start at the undergraduate level with Arduino board that you said is it cannot be used for AI application. You have to use GPU based board for AI applications.
okay.
Arduino boards they can be used for generic controls and stuff. But you can combine both. Like in my case, for CN Express system we have built, we are using GPU and the Arduino board together. Like, I mean, it depends on the system design actually. What task, what kind of mechanized or what kind of electronic control system you are building. For the AI implementation, of course, you can use boards like Raspberry Pi, the latest edition of that, and then you can use these NVIDIA's Jetson Orin Nano,
So,
those kind of boards, definitely. But I don't want to, yeah, but basically what I'm trying to say, you need to have a combination of GPU with another boards. And some people also like to use FPGA still.
okay.
FPGA based boards are still being used, but it depends again on use case scenario and of course the cost, like how much budget you have and how much you are able to willing to afford to buy those high end boards. Yeah, it can play a lot of factors actually play in that.
Yeah, okay. So I think in that box I have seen one question. Shall I go with that? Okay, the question is from the chat box. There is a question: how far AI in prediction are working in the US?
How far AI yield predictions are working in India and US? What does this mean actually? How far?
What is the accuracy of the AI algorithm
Oh,
which are predicting?
I mean, there is no specific answer to that. It can depend. It can depend from farm to farm. But in terms of how much it is being used, yes, it is. It is. People, farmers and growers are using because all these tools. There are a lot of companies actually, and they are like for example, John Deere itself is provides yield prediction tools like growers can log in into their platform, and they are making the prediction of their yield all the time. And at the back end, they are using AI. So and this is just an example. Syngenta is doing, Corteva is doing, AgriScience, this Bayer is doing. So all these big tech, agricultural technology companies, they have all these tools where the growers and farmers have accounts. They go and they are making the yield prediction all the time. So AI is being used heavily, actually. Yes. If that is the question he asked, like how much it is being used, but how far that it's very difficult to say what exactly he means by how far. Accuracy wise, of course, uh, it's not like there is no any right answer to that. Like some growers they trust those values that comes, and some growers they don't trust that. But the idea here is it gives you some perspective or at least some range. Okay, this is the amount of yield that you might end up getting, with some of course plus minus, right? Because there's always some error associated to that. So that is always there is some boundary for some room for error all the time. But yeah, it is being used actually. There is another question I can see from Dheeraj Tulaskar. Implementing IoT-based farming in India faces challenges like poor infrastructure, high cost, lack of awareness, fragmented land holdings, and limited digital literacy. How to overcome? Yeah, this is another excellent question, and I try to actually answer this actually in the slides. But again, uh, the first way to answer this is university as you are playing the roles. Here in United States, most of these agriculture universities, they have extension based positions. Now what these extension people do, their job is to communicate we as a researcher, to communicate our information to the local farmers and the growers about the research that we did, how to translate our technical information into a very layman's term so that farmers and growers can understand about the research findings, and how to train them so that they can use, okay, this, our researchers at this university, this is what they did, this is what they found, and how can they implement in their day-to-day farming practices. That's their job to do that. So if Indian universities, they can start creating these kind of positions like extension-based positions, and they can start training the local growers and farmers in their language that they can understand from the researchers' language, like bridging that gap, that is going to be very useful, one step in that direction. The second most important thing is definitely going to be the help from the government policy makers. Like they need to create and provide some way to subsidize those farmers who are trying to implement these kind of technologies, right? So if they are using some precision agriculture technologies, they are basically going to cut down the impact on the environmental, negative environmental impact. So this is ultimately helping to reduce the pollution in the whole country and conserve the resources. So government should subsidize those farmers who are able to implement this kind of technology or who are showing some willingness to adopt these technologies. So it has to streamline that process so it becomes affordable for them. So that can be one very useful step in that direction. Digital literacy, of course, training more and more, encouraging, because I think in India and in the world in general, it happened in the United States in the, I think after Second World War, that a lot of labor people started moving into general service sectors rather than farmers. And what happened then, we started having labor shortages. In India, what happens is like nobody wants to be farmer. Like if you are like, the perception is that if you go to university degree, if you get, you have to be in the service sector or engineers or doctors itself. There is no concept that even by being educated, getting a university degree, you can still do farming practices in a very better way. So if we can educate and train the people that no, you can farm even after getting a university degree, then that's what going to take one big step in terms of that. Yeah. I hope that answers to some extent.
So I think we do not have any questions there in the chat box itself. So I want to hand over this to our today's program coordinator, Devendra Goyal sir. Sir, are you there?
Hello, good evening, sir.
Good evening.
Dr. Yadav, thank you for accepting our invitation and sparing your valuable time in your busy schedule. Thank you very much, sir. And we will be associated in future too.
Yes, sure. Thank you for having me once again. And I would like to thank your whole team for giving me this opportunity to talk some of these aspects. So I'm really delighted. So thank you. Thanks to all of you. Yeah.
Yes, thank you from our whole CSMSS family and management. And I also thanks to AICTE also for giving this opportunity for us. Thank you, sir. Thank you.
Thank you. Thank you very much. Have a nice day. Have a nice evening.
So thank you all the participants for your presence for both the sessions. So now we are going to close this today's session. The feedback link of the today's day, I'm going to share in the WhatsApp group. So because we are facing some issues while putting the link in the chat box of the Zoom, so I will put the link in the WhatsApp. You can do the feedback afterwards. Okay. So thank you all. We'll meet tomorrow at 2 p.m. We have a first 3 sessions are there, and then we have a feedback session and test will be there. After that, we'll have a then final validity session will be there. So thank you all, and then good night.
God, there's this phone app.